Okay, welcome everyone to the second day of ST4. Just to remind you that during the lecture is going on, if you have any questions, you can just simply unmute yourself and say that you have a question and wait for the speaker to acknowledge your interruption and then go ahead with your question. If already a question answer session is going on, you can use the raise hand feature to notify the hosts and the moderators that you have a question and wait for us to call you on. And otherwise, you can also use the chat feature to ask the question. So today we'll be started off with the second lecture by Biswajit Sahoo on soft theorems. Biswajit, over to you.
Okay, thank you. Welcome back to everyone. So let me first recap what we have discussed in the last lecture. So first, what we are trying to do in this set of lectures is in the first at least 2-3 lectures, I will try to give a derivation of the soft photon and the soft graviton theorem in a generic theory. So for that, we made some assumptions to derive this soft photon and soft graviton theorem. So basically, we made 2 assumptions in the last lecture. One is that we assumed that we have someone has given us a one particle irreducible effective action for a generic theory, and then basically we will covariantize this action to derive various vertices and propagators, and then basically using these vertices and propagators we want to compute Feynman diagrams, and then try to see that if we take soft limit when the momentum of the external photon or graviton is small, we can expand the amplitude and try to derive the factorization property of this amplitude. So the next assumptions.
I had a doubt about this.
Okay.
So when you were writing, giving this prescription that you have to replace all the usual derivatives with covariant derivatives and so on, you necessarily have to choose this projected to the Lorentz coordinates, right?
Right.
But I'm slightly confused. Like if I just start with the small perturbed metric, which is some eta plus small s mu nu, like you're writing.
Right.
Then the choice of that E alpha A's are not really unique, right?
Right. So what we are doing is basically, in a sense, like if someone has given a theory to you with all the interaction terms, then just you can use this theory to just compute Feynman diagrams, and you can compute the amplitude.
Yeah, but
here,
sorry, go on.
Yeah, so here what I am trying to do that, suppose you don't have enough information of the theory, like you don't know what are the what are the kinetic terms of the particles involved in the theory, and what are the interaction terms. So for a more generic theory, it can be scalar, like for soft photon theorem, it can be scalar QED, or it can be like spinor QED, or maybe it will have some higher derivative correction. So a more generic theory, we don't have the full information of the theory. But still, since we know that the soft theorem, like from earlier understanding that people computed in different theories and get the same soft theorem, so people expected that those one can derive even in a theory independent way. So here, basically, we are trying to do in a theory independent way. That is why to get the coupling to the soft particles to the finite energy particles, we use this covariantization technique. If you consider a particular theory, then you don't have to covariantize it. You have already all the interactions, like what you are telling, like the metric, if you take eta mu nu plus 2h mu nu, then you already get the couplings of this theory, and just you do the Feynman diagram computations.
No.
So this is the main difference.
Okay. I'm just confused. Like, how do I choose a unique E alpha mu's, like the anbinds or whatever the real binds, whatever, given this small perturbed metric and such.
Okay. So first of all,
from a metric, if I just look at the small dynamic perturbation metric, like eta plus s, there's no unique E alpha mu. But if I was just a naive flat space scattering scattering process observer or something, I would think there's naturally a frame associated with the and directions and everything already decided by some asymptotic flat space observer. But now you're saying you have to correct the metric. But once I look at the corrected metric, I'm confused. How do I come up with a unique choice of E alpha mu's, which matches with the notions of a naive observer who thinks, okay, like there is a flat space eta coordinate system already fixed, but he has to choose a correct time frame which matches with it. I mean, I guess the answer is there's probably a prescription to like choose the correct Wheelbine, or probably it doesn't matter. I mean, maybe some coordinate, I mean, whatever, all choices gives the same answer or something.
I think all, first of all, all kind of choices gives the same kind of answers, but you can, means the thing is that, first of all, I think one point I want to mention that what you told, that this is small metric fluctuation S mu nu, this is not true. This S mu, like whatever you have the metric, you can think of this G mu nu and just subtract from eta mu nu and divide by 2 and call it S mu nu. So we are not even thinking S mu nu to be small. Now you can think that then why I am expanding about S mu nu.
No, that's okay. You can expand around any G. That's okay. Then also I'm confused, but because you're kind of correcting the Lagrangian for small soft background, right? So
right.
And so one, I mean, if you start with the corrected metric, I don't see how there's a unique Wheelbine. But if you really think of like starting from the background and correcting it, I feel like there should be a unique Wheelbine.
Okay. So I am choosing, yes.
Can I ask a question? Why should there be a unique Wheelbine? I mean, because Wheelbine has like additional indices compared to the metric, which are local Lorentz indices. Right? So in the tangent space, you can do any rotation, and that is what makes the Wheelbine not fixed given a metric, right?
No, like maybe if you're my issue is like I thought the Wheelbine, if you're thinking about like a flat space scattering process, the Wheelbine is fixed by the orthonormal, the Lorentz directions are fixed by the usual Lorentz directions for the observer. That's already fixed. In that sense, there's a unique Wheelbine. No.
Okay, so like I think the way mathematically it goes, like I can say, is basically what I am doing in a sense is so I know the relation of the Wheelbine and the metric, and now I am choosing the background metric, and as if like fluctuation about the asymptotically flat metric, like, or the flat metric, and I am calling this G mu nu to be eta mu nu plus 2S mu nu, and this is related to the basically this Wheelbine in this through this relation, right? And so what do you just consider that? So a small fluctuation of E to be some E tilde mu A, like some delta, you call this thing to be delta mu A plus some small correction, say delta of E mu A, and just substitute this expression and try to derive what will be this delta A mu A up to the linear order in S, and you will find that it will be just S mu A.
Is that a P A mu? What did you write a P A mu? What is that?
No. This is some small fluctuation of delta. So let me call, maybe it's delta E.
No, the first thing is a delta A mu. Flat space.
Yeah. This is a delta. Okay, sorry.
Yeah, but so now what I'm confused is like I could still have a maybe like I don't know if it's the same way to say it, but like you could have a soft graviton back. I'm slightly confused if this is unique or it
can I make
matter.
a small comment?
Sure.
Yeah. Suppose you have a background gauge field, right?
Mm-hmm.
So when you have a background gauge field and you want to covariantize your theory with respect to that,
right,
the choice of the gauge field is not unique. It's up to the gauge freedom that you have a unique gauge field, right?
Right.
Sure.
So different observers can have different AMUs, but if they're related by some gauge transformation, then you call them that they're the same background field. So it's the same here, right? Different Wheelbanes, just as long as they're related by diffeomorphism, is the same soft background.
Actually, I'm even more I would like to emphasize it even more that, all these are like fields, and what you measure are like polarizations, which are like on-shell degrees of freedom. So whatever Wheelbine you choose, the on-shell degrees of freedom won't change. Just like whatever metric components you choose, there are 10 components, but ultimately you have 2 polarizations, right? So similarly, there are 16 components of the Wheelbine, but then there are 10 local Lorentz transformations, which will be gauge fixed when you compute the on-shell degrees of freedom. So I don't think it matters what are the off-shell number of components.
Yeah, maybe the question is in the off-shell covariantized action, it may differ between 2 different choices, but the on-shell amplitude, it will give the same result.
Okay, I think off-shell also, like, I use the term badly, like off-shell degrees of freedom also we will see in my lecture, I think today, that you take the number of components of the field and subtract the number of gauge parameters.
Right.
So once you do that, it's just that EA mu has like 10 more parameters corresponding to local Lorentz transformations on the tangent plane, because it has the index A. Right. So it has 16 components, but when you subtract not 10, 6 more. 16 components, and when you subtract 6, you get 10, which is that of the metric, and then you have to subtract diffeomorphism and so on. And then for going to on shell, what you do is you do residual gauge fixing, so you subtract 4 more. So then you get 10 minus 4 minus 4, which is 2. But I think ultimately metric has 6 off-shell degrees of freedom and Whalebine has 6 off-shell degrees.
No, I agree with all that. Like I think I can follow the degrees of freedom counting and so on. I'm just saying that in this case, if you think of an asymptotically flat space observer, but then correcting his calculations for a soft background, there's a preferred gauge, which is the Lorentz frame he thinks the flat space already had. Now, if you boost him and change it, then you can that changes and you can do all stuff covariantly. But for any observer, there's a so I was just confused because we started with the action where derivatives were all taken by some flat space observer, but then he was asked to correct it for a soft background. But now he has a preferred gauge, right, where he thought the usual Lorentz directions are already on the manifold. But now he has to correct it for the soft background. So I'm just asking, if I start with the RHS of what Biswajit wrote for me now, how do I uniquely select a preferred gauge, I mean the natural gauge for him from the right hand side? Because from the right to the left, I thought it's not unique.
Why did he have a natural gauge to begin with? Because it was flat. But that also has Lorentz transformations, no?
Not local, not local, only a global Lorentz transformation.
Why can't one do a local Lorentz transformation
when you select? I thought I can't. Okay.
I see. Okay. Yeah, maybe. Yeah. Okay. Yeah.
So from the RHS to LHS, I don't see a unique way, but I thought there should be a unique way to do this, and because I'm a flat space observer correcting my calculations.
Okay. So what I can tell, I think, is that if you choose suppose particular frame, and if they are basically asymptotically, you have a eta mu nu to be metric, and then you are basically gauge fixing it in the background, and then you have the one pay gauge gauge covariantized effective action. Now I think this gauge covariantized effective action is Lorentz invariant and both gauge invariant. So in a sense, after getting the action, whatever you try to do from this, so this will not be affected how you changes your background or which kind of frame you are.
My worry is it's also local Lorentz invariant, and hence I don't know what. I'm just asking, what is the gauge? What is the way to put the gauge condition which will match with the naive flat space observers coordinate system? Naive flat space observers Lorentz coordinate system.
Okay.
Maybe I'm asking what's the gauge condition?
So I will use basically the Lorentz gauge condition, so that I didn't need. So what I will use is basically, let me.
You can. I guess that you can do for the calculating the metric degrees of freedom and so on. But you need to choose a preferred Einbein, Whalebine.
Whalebine, right? Yeah. So for that you need a particular choice of the Lorentz frame you are telling.
Yeah, I'm just. I thought so, but
actually I'm a bit confused, because even if you have flat space and what you want to get in the end is eta mu nu, right?
Right.
So and the way you do that is delta a mu eta ab delta b nu. Okay, and then you can do a local Lorentz transformation. The metric will still remain eta mu nu. So I think it can be done.
Okay.
Okay, maybe we can discuss it later.
I have a slightly different question or something. Just a bit of. So you started out with some generic theory, and then you sort of integrated all quantum fluctuations and got a 1K effective action.
Right.
So I mean, in the theory that you started out with, you could in principle have gravitational degrees of freedom.
Right. Exactly. It have. Yeah.
Yeah. So now once you have a 1K effective action, I'm confused what is happening. Did you end up with eta mu nu and asymptotically flat background?
No.
Have an arbitrary metric, and then you're just decomposing it to eta mu nu and S mu nu.
Right. What I am doing is that in the 1P effective action, it has obviously a curved metric, right? You have a metric which also has that I am calling to be H mu nu. And what I am doing is that I am expanding this metric about all the fields vacuum expectation values, right? So what I am calling is that for the gravitation field, whatever they have, I am calling this G mu nu to be eta mu nu plus 2 H mu nu, and I am expanding about the H mu nu. So this H mu nu will play as a hard graviton, finite energy graviton. And now this I will treat as an extra field which already has a finite energy fields. Now in this background, I am covariantizing with respect to soft background. So hard graviton is there already, which is there present in the theory.
I see. So this is additionally you're adding a field S mu nu.
Right, exactly. Which is a low energy graviton.
I see. Okay.
I think it's fair to say that the total metric is eta mu nu plus H mu nu, which is hard graviton, plus S mu nu, which is soft graviton.
Right.
That's the total metric.
Right.
Yeah, but I am treating in a sense H mu nu to be a different field since I expanded about the eta mu nu. That's why I was covariantizing this with S mu.
Okay.
So let me proceed. Then what we have made one of the assumptions is that now if I covariantize this action and try to derive any vertex, and suppose this vertex involves one or many number of soft photons or gravitons, I'll assume that this kind of vertex should not contain any 1 over soft momenta or any power of soft momenta in the denominator. That that will be one of the assumptions. So then, like with these assumptions, so after expanding all this 1P effective action and gauge fixing the action, I have taken this general form of the effective action to be this, which you can see started from 2 fields to arbitrary number of fields, and there are for n equal to 2 you will get a kinetic term, and for n greater than 2 you will get all the interaction terms. And phi alpha I have taken to be set of all fields present in the theory, which you can think of remains in a reducible representations of the Lorentz group SO1, D minus 1. And this alpha index basically contains, like, if there are different particles, so it takes care of the different particle index as well as same particles polarization indices. Then what we have discussed, the covariantization procedure, where basically we are changing now the flat metric eta mu nu to beta mu nu plus 2s mu nu. And the other thing is that I am changing the ordinary derivative which are there inside the V, like V is written in the momentum space, so it is a function of momentum. So that in coordinate space basically you can think of comes from some derivative operating on the fields. So if such kind of terms are there in the action, you have to covariantize those, and that you can do is basically A's are basically the tangent space indices, and mu, nu, all these indices are curved space indices. Curved means in the soft graviton background indices. And then you basically make this ordinary derivative to be covariant derivative. And so we have symmetrized it. You can symmetrize it. And if you don't symmetrize it, the difference between them will be Riemann tensor or higher curvature, like derivative of Riemann tensor and all these things. And since those contains more than 2 or more than 2 powers of momenta, those will only affect up to the subleading order. I am here concentrating up to only the derivation of subleading soft graviton theorem. So I'm just not taking care of those terms. And I have given here what will be, if there is a single covariant derivative operating on a field phi alpha, what will be its expression. So since I am covariantizing in respect to both soft graviton and soft photon background, so you can see, like, this is the basically covariantization, and due to the covariantization with respect to soft photon field, that will be the term will be there. And for the soft graviton field, this is the term where omega mu AB is the spin connection, which up to linear order in the soft graviton field turns out to be this expression. And sigma AB is basically the spin, like the Lorentz generator of this field phi beta. Okay, so this is if there is a single derivative. If there is a double derivative, then obviously the one will have extra contributions associated to the Cristobal connection because of the 2 mu nu index. So Then what we have seen is that like what will be this like if this covariantization procedure is this, so what will be its momentum space expression for this covariantization? For that, I have given an example. If there is a single derivative, how the covariantization procedure works, and expanded all the terms in terms of only kept up to the linear order in the gauge field and the soft graviton field, and also only the linear derivative over only the single derivative over the graviton field and the gauge field, because if there are more derivatives, then it will contain more soft momenta, and you want to study up to the subletting order. And momentum space analysis of this expression, if we try to look, so this basically turns, since there is a derivative over phi alpha in momentum space, this basically turns out to like P of phi alpha basically goes to some polarization dependent terms and some spin dependent terms of the finite energy particles. So I will denote epsilon mu to be the polarization of the photon, epsilon mu nu to be the polarization of the graviton. This is the plane wave basis the expression is written. And then this, if you just substitute this expression here, you can get this expression. The momentum have to be shifted in this way. This is what covariantization in momentum space translates. So then in the last few minutes, we have discussed that now suppose we covariantize the action, and we have all the information about the Feynman diagrams, well, all the vertices and the propagators, all the ingredients we have. For deriving single soft theorem up to subleading order, what kind of diagrams we need to analyze? So I have shown that two kind of diagram analysis would be enough. So the first kind of diagram where the soft particle is attached to only the external line. So any of the external lines. So what will be the advantage of this thing? If the soft photon or soft graviton attached to external lines, then it will have a propagator with momentum pi plus k. And if none of the vertex factor contribute 1 over the soft momenta, then basically this diagram will contribute like 1 over k. So let me call k to be some omega n mu. Omega is the energy of the soft particle. Then you can think of this will contribute like 1 over omega, start contributed to 1 over omega. And if the soft photon or graviton is connected to some internal line, which is the diagrams, which is basically complement of the first kind of diagram, then it don't have any 1 over soft momenta contributions coming from the propagators. So it will start contributing only at the subleading order, which is basically order omega to the power 0. So, and this obviously first diagram also starts contributed to the leading order. It can have also the subleading contributions. So we have to analyze these two kinds of diagrams. So just to note that for explicitly computing the first kind of diagram, what information we need? We need only the information of the 1 pi vertex associated with 2 finite energy particles and 1 soft particles, nothing else. And the next kind of diagram, even we don't know such kind of vertices, but that could be only derived covariantizing the amputated Green's function, which don't contain any soft photon, which I will describe, soft photon or graviton, which I will describe later. So the next goal will be to derive the expression for so I'll use the notation that all the particles are ingoing. If the if some of the particles are outgoing, then just you have to flip the energy and the momentum of the particle to get the result. And also you have to flip the charge convention. Like if the charge is q for incoming particles, then I am using only all the particles are incoming. If you try to get the if some of the particles are outgoing, you just flip the momentum of this particle to be p2 minus p and the charge q2 minus q. Okay, and then okay, so I want a vertex which is a 3-point vertex. Okay, so from where this kind of vertex I can get, you can see that for getting this kind of vertex, I don't need the full one gauge fixed 1 effective action and try to covariantize. Only the quadratic part, which is what I have written, the n equal to 2, which is only the quadratic part of the effective action, which contains this vertex V2, which is basically the kinetic operator. So just covariantizing this thing, I can get the information about this kind of vertex. I don't need to covariantize the other higher order vertices. Okay. So I will call this V2 from now on to be some kappa. So this will be the kinetic term in the 1P effective action. So only covariantizing the kinetic term with respect to soft photon and the soft graviton background would be enough for computing the first kind of diagrams. Okay. So the generic expression for the quadratic piece of this 1P effective action has the form So this is the general form of this 1PI, like the quadratic part of this 1PI effective action. Just I am denoting V2 by this new K. Okay, and it has polarization, two polarization indices contracted with the two of the fields phi alpha and phi beta. Now you can see before even covariantizing, let us see that how much information we can extract from this expression for K. So first, yes.
I just missed the last argument that you said. Why only quadratic? Why not the cubic?
Oh, because like you see, so I have to compute these two kinds of diagrams. Okay.
Right.
So like first, let me focus on the first kind of diagram. So in the first kind of diagram, you see that I need a vertex where basically two scalar lines and one soft particle is attached.
Right.
So for getting this kind of diagrams, I need only a I need to only covariantize the quadratic part of the effective action, which contains two phi, because this is one of the phi and this is one of the phi and this is one of the soft particle.
Right.
Right. So it is enough to covariantize only the quadratic part.
I see. Okay.
Okay. Now you see, so this is the action. So first of all, if we just let me consider that this phi, so this phi can be Grassmann, odd Grassmann, even both. So you can change the phi to be, you can move the phi alpha to be right to phi beta and bring phi beta before phi alpha, and you can redefine, like you can change your alpha beta indices, but you want the accent should remain same. So if you demand this thing, you will get some condition on this K, and it translates to the fact that you will get that K alpha beta of Q2 should be K beta alpha of minus Q2. So in matrix notation, like in index P notations, what I will use later is like this to be K transpose of minus Q2. Okay, this is one of the thing just from the symmetry, just from the action you will get, because we have to basically here it seems that we basically symmetrize this K properly in the kinetic term. The other thing is that we want that this whatever this quadratic part of the action, that should be invariant under SO2 transformation, SO2 global transformation, because we want that it has a global SU2 transformation and global SO2 transformation, which is basically equivalent to the U1. And since we are using real representations for the Lorentz group, so that's why I will consider SO2. And the generators of the SO2 transformation, we already told this is the Q alpha beta, which we have seen. In a sense, like under this transformation, phi alpha goes like e to the power I u some theta. Theta is the parameter of this SO2 transformation, alpha, beta, phi beta, right? So this action should be invariant under this transformation, and that will give another constraint on K. And it basically turns out that the constraint it becomes is basically Q gamma alpha K gamma beta plus K alpha gamma Q gamma beta have to be 0. Which also I can write in a index free notation, which basically translates to Q transpose K plus KQ equal to 0. So these two properties, before even covariantizing, like we can get that K have to satisfy, and you can check that for any general theory. If you take the kinetic term, and if it has SO2 invariance, then it will have the second property, and if it's like just from the action, you can see that the first property will always hold in momentum space. Okay, is it clear?
Sorry, I missed the part about SO2 global.
Okay. So what I am telling is that, like, from the beginning, I will consider this phi alpha to be some real representations of Lorentz group. So, like, if you have a complex scalar, say, you can write down the action like phi star box plus m square phi, okay, to be your action. But what I will do is that I will write down phi to be phi 1 plus I phi 2, and phi star to be phi 1 minus I phi 2, and I will write down this phi to be like the phi alpha, which I am telling is a column vector with phi 1 and phi 2, and I will try to write down the action in that form. That is why it means that the U1, whatever the U1 global transformation is there, that is manifested in the action as a SO2 global transformation.
I see.
And so Q is basically the generator of this SO2 global transformation.
So this relation is basically the invariance of your S2 under this thing, right?
Right, under SO2 global transformation.
Okay, fine. Sorry, yeah.
Yep. So I think let me copy this thing to the next slide. So now this is the quadratic part of the 1pi effective action. So from there you can derive what will be the propagator of the field phi. Because what will be the propagator, you will expect that will be basically the inverse of this kinetic term, since it is already written in momentum space. So taking inverse is not a problem. So the Feynman propagator with momentum q is basically chi. So let me use the index say alpha beta. That will be chi K inverse matrix q with alpha beta index. And we know that, like, if this is a massive particle with mass m, so that will have a pole, this denormalized mass m. So we are already integrated out the quantum fluctuations. So we'll expect that this will have an expression like this: q square plus m square, plus there could be some numerator factor, and the numerator factor I am calling to be xi of q. So that defines the xi of q. Okay, so maybe so all the signs are, let me remove this thing. So that this is the xi expression. Okay, or maybe cascade, I don't know. So this is the propagator for the finite energy field. You can derive from here. Now let us covariantize this 1pi effective action, the quadratic part. Okay. So I'll just directly first write down what will be the form of this covariantized part. Then I will explain how different terms are coming in the picture. So first let me write it down. So let me maybe make this a little smaller.
Biswajit,
Yes.
I have a slightly naive question, maybe not exactly related to the theme, but when you have the 1pi effective action, you've integrated out all quantum fluctuations,
Right.
and then essentially, basically, you have some sort of some sort of an action type of thing, but it's essentially classical, right? Once
Right,
you've
right.
done that, I mean, so when now, why do you have a Feynman propagator and not a Green's? I mean, like an advanced or retarded Green's function?
Okay. Yes, still means the thing is that probably since I will compute always tree-level diagrams, so it will not matter whether I will use Feynman or retarded, because I don't have any loop to integrate out, so it will not matter. But I think in quantum field theory, like one uses the Feynman propagator, and so one will get the same answer. It will not matter for tree-level amplitudes. That I can say.
Okay.
And yeah, but and also since I am computing in a sense, it already contains the loop amplitude. So basically, I am using the same notation as a Feynman propagator. Yeah, I can.
Okay. I see. Okay.
So if we just covariantize it, so that will be a action which involves 2 fine energy particles and 1 soft particles. So let me just quickly write it down. This is a huge expression. Then I can explain each of the terms separately. So you see now you have extra field with momentum k, so that will give a extra momentum integral, and the delta function will also get corrected by this extra momentum. This is the just the Poincare invariance will suggest this thing. So q1 plus q2 plus k. Then you have this phi alpha of u1, and then now you covariantize this kappa, whatever we have the kinetic term, and what we have seen is that the kappa is function of q2, and what we have seen is that covariantization basically shift q2 by some amount depends on the polarization of the photon and graviton. So basically what we have to do, you have to basically use this relation and shift it. Okay, and then and after shifting, so you just replace q2 by that expression, and then just expand it in power of like the epsilon mu nu and the epsilon mu, because I want, like, it can contain many terms like 2 epsilon, 3 epsilon, all these terms, but I don't need to get the single soft graviton theorem. But if you want to get multiple 1 or 2, then you need a vertex for suppose 2 graviton, 2 scalar, then you have to keep this kind of terms as well. But for single soft graviton theorem, I will keep only the terms which are linear in polarized sentences. So this is a huge expression. Let me write it down. Okay. So this is the expression what you will get after covariantizing and keep up to linear order in momenta and also single polarization tensors. So let me explain each of the terms, how they are coming in. Okay. So the first term you can see is basically translating the momenta q by, so let me, like the first three terms are basically covariantizing with this due to the covariantization with respect to photon background, and the last two terms are basically first two terms, actually this and this are one term. So first two terms coming from the covariantization of the covariantization with respect to soft photon background, and the last two terms are basically covariantization due to the soft graviton background. And you can see the first term is basically you are shifting the momenta q2 by minus epsilon mu, and then q2 mu by minus epsilon mu q gamma beta in a sense. And then basically that means basically you have to basically the kinetic operator some momentum dependence. So you are, if there is a linear term, you are just removing this thing by taking derivative of del q, and whatever you have the translation, you just putting this back. Similarly, the second term coming from basically the, if there is two derivative or the two momentum part in the kinetic operator k, then that will have, like I have written down the expression of how d mu covariantization happens, and that contains some derivative operator for the first d mu, say on the second d nu there is a gauge field operating on this thing. So this kind of terms are there where some derivative is operating on the gauge field from the, if there is two derivative or the two momentum dependence in the kinetic operator, and that gives the second term in the covariantization. Third term, this is the term which basically comes from the leading order covariantization with respect to the soft graviton background. It is telling basically the q2 have to be shifted by epsilon mu nu q2 mu have to be shifted by this thing. That basically coming from this term. And the next term is basically the spin connection term which we have. Basically the omega, like the omega mu AB term, and that omega mu has a derivative over the S mu nu field. So that's why there is a momentum dependence here corresponding to this polarization tensor. So this turns out to be the expression after covariantizing this. So is there any question?
So algebraically, how are you doing this? So you take k alpha beta to be q2 plus k, and
Right.
then you Taylor expand it, and then replace k mu wherever you have instances of k nu in the expansion by your previous prescription of covariance.
No, I think it's a little more involved, like
please.
So okay, so let me say, like here you can see in momentum space what it is telling, that if there is a PA, so just look at for a moment leading order.
Yes.
So if there is a PA, that you have to replace by PA have to be replaced by minus epsilon a P mu.
Yes, the entire thing, right?
Right, and the some other terms also that contains polarization index. So that means basically if you have a function, say function of P, so for the leading term, what you have to shift the function to be under covariantization, the function goes like P minus, say, if it say, let me say it's at some index and mu P mu, right? So that basically you Taylor expand in a sense.
Yes, exactly.
Right.
Exactly. Yeah. So this is what I was.
Yeah, this is what I am doing, and then basically, like you have all the other terms which depends on all the polarization tensor. There one have to take care of the indices of this k alpha beta, because this is a scalar function. I have taken AFP. If it is some other scalar spinor indices, you have to take care of this term. Okay. So now, after having this expression, you can find out what will be the vertex would be. But just I want to mention that this is not, like, probably this is enough for the soft graviton background to get the kind of vertex which I am telling to finite energy particles and to like one graviton. But for one photon up to the linear order in K, this is not enough. So, but you can have a term which is, since you see by gauge invariance, one can couple arbitrary way to the F mu nu of the soft photon field to other fields. So that term one cannot get just by this covariantization procedure, because this is gauge invariant by itself. So that one have to add by hand, and theory to theory that term would matter, and that term will affect the subleading soft photon theorem. So the general form which one have to add by hand, which is basically linear in, which will be linear in the momentum, like linear in the momentum of the soft photon. So let me write this S3 bar. So this is really called the non-minimal coupling. So one can have okay. With this, you can always add a term Q2 phi beta for Q2. So you see, this one cannot get by the covariantation technique because this F mu nu is already gauge invariant by itself. So one have to add this thing by hand, and then basically for different theory, one will have different functions C alpha beta, and then that will have a different, that will give a different contribution to the S3 bar. Right? For example, in spinor QED, you can have a term like in the action in coordinate space, say like psi bar, sigma mu nu, psi f mu nu kind of term. This is one of the example of non-minimal coupling, and it can have arbitrary coupling constant. So here C basically is the commutation of the two gamma matrices, and there can be for other theories one can add such kind of terms. So this gamma 3 vertex what we've defined for two finite energy particles and one photon or graviton, that to derive this thing for one external soft photon, one have to include this term also in the effective action, in the covariant effective action to get the vertex.
Sorry, Biswajit,
yes.
What are the properties you assume for f mu nu of k function?
Okay, so f mu nu is basically f mu nu of k is defined to be, sorry, I should write it down. So let me. This is k mu epsilon nu minus k nu epsilon mu. So this is uniquely the field strength. The property of the C alpha beta there have to. C alpha beta is arbitrary function. So there will be, there on have to use some property of the C alpha beta. That's obviously C alpha beta. Okay, actually I have not contacted all the index. Sorry, C alpha beta mu nu. Sorry. So mu nu is contacted with the F mu nu. So the C alpha beta obviously will be like antisymmetric in mu nu index, and also this action have to be global SO2 invariance. So that will also give some property of the C, that like Q transpose C plus CQ have to be 0, right? And also like, since you can, like if this is Grassmann even or Grassmann odd, you can flip this phi alpha and phi beta depending on this thing, there will be sign. So probably in the last slide I have given the result only for Grassmann even. Maybe I should put here a plus minus, plus for Grassmann even and minus for Grassmann odd. And also here this C have to satisfy a similar property, that say C alpha beta of Q have to be C beta alpha of minus Q minus K. Right? So these are the properties C will satisfy, and F mu nu is the field strength up to linear order in the polarization tensor. Is it fine?
Yeah, okay, thanks.
Okay. So now you have this, both the action, now you derive what will be the vertex factor. So I want to derive, say, this. So let me.
Biswajit, you have stopped sharing.
Okay. It's not working. Okay, let me then.
I think your iPad got logged out.
Yes, yes, yes. So. Okay, I am not looking to the question like the chat box. So if there is some question, please
Yeah, we will
tell
let
me.
you know. Yeah, we'll let
Okay.
you know.
Oh, sorry, it's to save it from my iPad itself, right? Is it visible now? No, probably.
Biswajit, your iPad is no longer in the participants list. I think you need to log in through your iPad Zoom again.
Okay, okay, okay. Can you tell me the password and the ID, please?
Just a second. Yeah, the ID is 813
813
7195
7195
5520.
5520. And the password?
705
705
423.
423.
Keep your audio off on the iPad.
Yeah.
You can share now.
Yeah. It's not happening.
Sorry, what's not happening?
The sharing is not working in the iPad.
Just try again. I think you started before I made you a co-host.
Okay, okay. Okay, it's not happening. Maybe I should do from the
Sorry, why
laptop.
is it not happening? It's you have the co-host permission.
No. What is happening is that when I am clicking on the share screen, like the share, so it is not. It was showing Zoom, and I was clicking, but it is not working. Yeah, I don't know the problem, but I think maybe I am connecting to the.
Okay, let's try this.
Okay, now it is fine.
Yep.
Okay. So what are your? Sorry, something. Okay. Is it fine now?
Yes, please proceed.
Okay. So what I was telling in the last slide is basically like one have to add a non-minimal coupling action, this kind of terms with the earlier covariantized part what we have, and then use this sum of these two part of the action to derive the one pi vertex associated with two finite energy particles and one soft particle. So
just a small question.
Okay.
Yeah. So why we can't add non-minimal coupling for like gravity, like corresponding to gravitational fields?
Okay. So Okay, for the gravitational case, you will have a Riemann tensor, which is which will be coupled, and you know the Riemann tensor contains two derivatives of the graviton field, right?
Yeah.
So it is quadratic in momenta, and now you can see the kind of diagrams which I tried to compute is first kind of diagram, which has 1 over k from the propagator, and this will be the leading order. So in the subleading order, I can allow in the vertex only up to the linear order in the momenta. If I allow the quadratic part of the momentum, that will contribute at the subleading order. Since I am focusing on up to the subleading order derivation, I have not added this thing. But if you are interested to go up to the subleading order, you have to add this term also.
Okay. Yeah, fine.
So then how one can derive this vertex? So alpha beta p minus k, that one can just derive using I del del phi alpha then p and del del phi beta of minus p minus k operating on this S3, the covariantized part of the action, plus also the non-minimal coupling part, right? So, and also depends on the soft particle also. So using this like action part, whatever we have given, you can derive what will be the expression for the gamma 3 alpha beta. And this is also a long expression, and I'm not writing here. So in the note, it is there. You can see when I will upload. Okay. So now you have all these ingredients. Now it's you can try to compute the first diagram. So let me write down the expression for the first diagram. Let me draw it once again. So you have a gamma 3 vertex, and you have a amplitude gamma with all the other particles are there except the pi particle. And here is the pi momenta coming in. Okay. And this is minus pi minus k. So you can easily, so let me call this diagram to be A. So the contribution of this diagram you can easily write. So what will happen? You have to sum over all the part. This suppose photon or graviton connected to any of the line. So you have to sum over all the i's. Okay. And then also you have to multiply for the polarization vector of this particle I. So I am using matrix notation to write this expression, in a sense index P notation. So that will help me a lot. So for that,
Biswajit,
yes.
One question, probably I missed this part. When you expand this gamma 3 in terms of kappa, in terms of the small momentum k,
right?
There's this capital gamma also, right?
Right. So
that should also depend in principle on the soft momenta. Do you also need to expand that?
Okay, actually I don't need to expand that thing. So I have not explained why I don't need to expand, but I can explain now. So you can, so let me then go to the next slide. So actually you can think that why not I have kept, like I have only kept the spin connection part, but in the two derivative there could be a Cristobal connection. Why this kind of terms I don't need? So the argument follows like this. So like suppose in a general kinetic term you had a expression. So I'm just suppressing now all the other momentum integration and all these things. So let me write down. Suppose you have an expression, say in the after covariantizing, you have expression say phi alpha and some e a1 mu, e an mu, and then some mu1 mu n, and then some d mu1 dot 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 d mu n, and some phi beta expression and some alpha beta are contracted in some way. Okay, so I'm just focusing on this part only. So this is suppose the expression what you have after covariantization. Then what you can tell that, okay, so obviously in this there is many more than, when there will be more than one covariant derivative, the Cristobal connection will appear. Suppose in the earth position, there one have to sum over all the Cristobal connection terms one have, but one of the term you can see will be this kind of structure. say, and see when the crystal connection appears, already single graviton polarization already appears. So since I want to compute only the gamma 3, so I can substitute all the E's and all the other D's to be just ordinary derivative other D's and all the E's to be the deltas. Okay. So I can put here all this to be delta A1 mu1 and mu n, and some have delta mu1 to say delta mu r minus 1, and the rth place I have chosen to be the mu r plus 1 and some nu l, and then del nu r plus 1. Sorry, one of the derivative, yeah, it's fine, I think. One of the derivative goes with the crystal connection, right? And then dot del mu n phi beta. Right? This is one of the term you can get involving crystal connection. Now, since I want only up to the like single derivative of the graviton polarization and linear in graviton polarization, so I can use the full, all the derivatives are operating here. So I can integrate like integration by parts, and I can operate all these derivative over the phi alpha. And if I do this thing, you can count how many derivatives are associated here. Basically n minus 1 number of derivative, because one of the derivative I converted into gamma, right? So gamma obviously contains derivative of the soft momenta, but those I'm not integrating out, just integrating out the finite energy particles momenta. So these also you can write. So okay, so sorry, I have, so if there is a gamma, since all the indices are below, so crystal connection will contain minus gamma, because you know that d nu will contain in the covariant minus gamma mu nu, because both indices are below, so there is a minus sign already. And now by, if we integrate by parts and operate all the derivatives on the phi alpha, then with this minus 1 we already have, we will also have minus 1 whole to the power r plus 1 due to r minus 1 due to all r minus 1 number of derivatives, right? And then the expression will have look like all the del mu 1 to del mu r minus 1, del mu r plus 1 to del mu n operating on the phi alpha. And then you have this gamma nu l. So I don't want to keep the derivative over the gammas, because there will be then two derivative, that those I don't need. I only need the single derivative piece. So mu r plus 1 and then phi beta, right? This is what the expression will give. But if you, before expanding from starting from here, if you use covariant, like you have the full covariant form, you can use integration by parts. You now have a square root of g part also, and you can do a covariant, like you can integrate back all the derivative operating on the phi alpha. So if you do that, then what you will get a minus 1 whole to the power r factor, right? And then you will have an expression which basically will look like d mu 1 dot d mu n phi alpha, this thing, and then you have all these e's, and you have phi beta, right? Now here, if you just replace the rth plus derivative 2 by gamma, then you will get a minus 1 factor, right? And r minus, and you will, this expression and this expression will be same. So from here, if you just replace the r derivative, what you will get is the minus of minus 1 whole to the power r times the same part whatever I have here. Okay. So you can write in a sense this term as a sum over this term, and this term. But you see what will be the coefficient of this sum. Like one is minus 1 whole to the power r, another is minus 1 whole to the power r plus 1. So for any r, these two terms cancels each other. So if you try to write in half of this term, this basically cancels. So in covariantation procedure, one don't have to analyze this like contributions which coming from the gammas if one want to study up to the subleading order of graviton theorem. Is it understandable?
Yes, but if you go beyond subleading order, then
then one have to keep. In the subleading order, it will contribute.
Okay.
So since I am focusing only up to the subleading order, so I have not taken care of this thing due to this precise reason. Okay. Fine. So I have to compute this diagram, and let me write down the expression in terms of the partition and the propagator, how it will look like. So obviously this propagator I have written in terms of some xi upon pi plus k whole square plus m square, and use momentum like on cell condition for the pi, which is pi square plus m square equal to 0. So then you will left with 2 pi dot k, and then you have to multiply by the polarization tensor. So I am using index p notation. So this is transpose of momentum pi, and then you have to write down the 3-point vertex gamma 3 with which has basically polarization of the photon epsilon k, and the momentum are basically pi's and minus pi minus k. Then the numerator factor of the propagator, which you have denoted by xi for the ith particle, and this has minus pi minus k the momentum, and then you have to write down the amplitude gamma I of pi plus k. So what is gamma I am telling? So gamma I of say pi, that is defined as, you just multiply by all the polarization j not equal to I, epsilon j. So let me maybe put the indices here. So alpha I. So this thing is j alpha j, and then you have the expression for alpha 1 to alpha n of all the pi's and epsilon. So whatever you have the expression for the gammas. So this is the definition of this gamma I notation what I have used, and this turns out to be the expression for A. So is it fine up to now? So now, yes.
So you are considering till subleading order so far because you are doing it for photons as well, is it?
Right.
Okay.
Means
so
I can, yes.
What happens for photons at subleading order? Like it's non-universal, but does it factorize?
No, it's like some part of it don't factorize.
Oh, I see.
Some part one can show it factorizes.
I see, okay.
Like actually what happens is that from this kind of diagram one can show that it factorizes, but the other kind of diagram is there, so that actually cannot one cannot write in a factorized form.
Okay.
Yeah. So yeah. Now basically now you see that I have given all the gamma 3 expressions, and I have also given the xi expression, and gamma 3 expression basically has the form of the kinetic operator like the k. Right, so k, the kappa, which I call, this is basically the kinetic operator, and so gamma 3 is written in terms of the kinetic operator kappa, and this xi is basically the propagator numerator factor of the propagator, and this kappa and xi has a relation because this relation what I have written while deriving the propagator. So here it is. So here the propagator. So you see this kappa and xi are basically related, right? So in a sense, what this thing is telling that kappa times q and xi times q is nothing but I times q square plus m square, right? And you can take derivative of q and which have derivative of kappa and xi related to. So if you take a derivative, you can get the expression like del kappa del q mu say times xi to be equal to minus kappa del xi del q mu and then plus 2i q mu, right? So you will get such kind of expression. And you know that you can take another derivative which involves twice of the derivative of kappa, and you see how this will help. So this will help to make this, if there is some derivative of the kappa is there and multiply xi because the propagator has a xi factor, that will translate to basically that will use this relation to remove all the derivatives of the kappa to derivative over the xi, right? Because the vertex factor, if I so though I have not written down, so you see the vertex factor contains the derivative over the kappa and the second derivative of the kappa, and with this vertex factor, like you can derive from here the vertex factor gamma 3 and you have a propagator xi. So using this relation you can move all the derivatives from kappa to xi, right? This is one thing what you can do. The other thing what you can do is that let me write down one extra relation. So the relation is that the other thing what you can do is that you can like see the gamma 3 vertex that contains a sigma matrix, which is the generator of the Lorentz transformation that corresponds to the different spin particle, different sigma. So also what I want to do is that I want to move this sigma to the extreme left as much possible. So for that one can use this relation. So how one can get this relation I will explain. So let me write down the expression. EB and then plus EB del chi o minus P and del PA. One have also a relation, similar relation for the kinetic operator. Sorry. Transpose that will give you, sorry. So this kind of relation basically turns out to be the consequence of Lorentz transformation. Like you want that your action should be Lorentz invariant under Lorentz transformation. And that basically tells that like if you have a kinetic operator, if you rotate the polarization index of the kinetic operator and simultaneously you make Lorentz transformation on the momentum, then the total angular momentum conservation will give this kind of relation for the kinetic operator. So you have to use this kind of relation to move the spin operator sigma as much possible to the extreme right if you try to evaluate the expression for this diagram. Because you know this gamma contains derivative over the kappa terms, right? And also have some spin terms, all these things. And this, so basically to remove the derivative of the kappa to the chi, you use the on cell condition, which is basically the propagator relation to the propagator to the kinetic operator. To move the sigma matrix to the extreme right, you use this Lorentz, like the Lorentz invariance of the action from the expression what you get, basically the total angular momentum conservation relation, and that you use to evaluate this diagram. And if you do all this analysis, you will certainly get an expression which I can write it down, but before really writing it down, let me write down the expression for the second diagram, and then I will sum over these two contributions and I will write down that full expression, whatever you will get. Okay, so that will be the strategy. And the other thing which I forgot to mention, maybe at the end, you see the expression here have a polarization tensor contracting to the extreme from the extreme right? And you know the on cell condition, what will be the on cell condition? If there is a kinetic operator is there, you know that the epsilon I transpose kappa should be 0. This is what you know that basically from the on cell condition, if the particle I is on cell, if you have a kinetic operator, and that basically kills the polarization. In a sense, like in Dirac equation, you see that P slash minus small m operating on the US of P equal to 0. This is the analog of this relation for any generic field phi alpha, and it's for its polarization epsilon I. This is the more general relation of this. So you use all these relations, and then you can simplify this expression, and you can show that up to the subleading order soft graviton expression, like even for the first kind of diagram, you can show that it turns out to be completely independent of this kappa and chi. And this kappa and chi are basically the information of the theory itself. So if you get rid of this kappa and chi, then you are fine that you it turns out to be independent of the theory. Only it depends on the momentum, spin, and all these things which are the scattering data. But for the soft photon theorem, which I will, when I will write down the expression for the soft photon part, since it contains obviously a non-minimal term already, so you will expect that this non-minimal term is theory dependent. So up to, in subleading order, you will not able to get rid of all this kappa and xi. So this will add up with this extra non-minimal term, and it will define a full non-minimal coupling term. So I think it's frozen even. Is it understood? I think my screen is again frozen.
We could see everything.
Biswajit, we could see everything.
Sorry, actually, like I was changing the slides, but it was not.
No, it was changing the slides.
Yeah, maybe on your MacBook the internet was slow, but for us it was fine.
Okay, it's fine. So now let me like how to evaluate the second kind of diagram. Let me explain. This is gamma tilde, and when the soft photon or graviton is connected to the internal line, not to the external line. PM. So that obviously, like this, you see this gamma tilde will be a function of the momentums and the polarization of the fine energy particles. So that you can, so this, since this is just a function of the momentum of the other particles, and this contains only at the subleading order, since it don't contain a propagator which can give in a 1 over soft momenta. So only the like the in the derivative, like the omega to the power 0 or the momentum to the power 0 order analysis would be fine, and only basically shifting this PMU. Okay.
We can't see. I think it's a lag.
Yes. Okay. So you know that in the leading order, basically how the PMU will go to PMU minus, so P sorry, I should write PI. PI mu times epsilon mu, and if you have a phi alpha, that will give a Q alpha beta, phi beta, and
Biswajit, again, I think your screen is not showing.
I think it is lacking, maybe. I'm not sure.
Now on our iPads, the moderator can see it's appearing, but on your screen, nothing has appeared.
Yeah.
Okay. So what should I do? I should stop share and do once again.
Let's try that. Let's maybe also try to keep your video off and see if it improves the bandwidth.
Yeah. That's a good thing. Yeah, just my video off. Yep. So you can see that up to, since I want only the, like I don't want any momentum from the, because it starts contributing on the subleading order. So I just kept only the first two terms in the covariantized procedure. And if you use this thing, you can write down what will be the expression gamma tilde in terms of gamma. And the expression that if you using this thing, it turns out that gamma tilde, which is function of epsilon k, and then P1 to Pn, really becomes, you have to sum over, like you have to use the notation that are equal to 1 to n, all the polarizations. Okay. And then which is basically function of epsilon and p. So this is what I am doing is that now basically that diagram computation, you just can covariantize the amputated Green's function, which you don't have this k momenta or the soft photon momenta, and just by covariantizing with basically translating this momenta to be this way, you can just read out what will be the expression for gamma tilde only at the leading order, because at the leading order of this diagram starts contributing at the subleading order, right? So is it up to this point, is it understood? Is there any question? Otherwise, I will proceed. Okay, so let me proceed then. Okay. Hello.
Yeah.
Yes,
Hi.
we can hear you.
Okay. Okay. Just. Then basically summing over these two kinds of diagrams, you will get the, like, I will write down what will be the final expression, what you will get. So then basically the amplitude corresponding to n number of finite energy particles and one soft particle. Will take this following expression. I am trying to write in an index-free notation, which I introduced. So this will be the leading soft photon and the soft graviton theorem. This is the soft photon part, and this is the soft graviton part. You can see there is 1 over omega if the energy of the soft photon or graviton is omega. So this is the leading part, a leading soft photon theorem or soft photon and soft graviton theorem. And now I'm writing the subleading order contributions, what you will get. So let me. This is the universal piece of the subleading soft photon factor. Then I am writing the universal piece of the subleading soft graviton factor.
Hi, I have a
Hello.
question.
Yes.
Yeah, so this is the expression for both soft photon and soft graviton theorem, right?
Right.
So you have one soft photon and one soft graviton in the expression.
Right.
So, so what are the momentums associated to the soft photon and graviton? Both of them are k.
Yeah, both of them are denoted by k. Like if you want to get the soft photon theorem, you just drop the terms involving soft graviton polarization. Or if you want to get soft graviton, you just drop the polarization part, like terms involving polarization of the soft photon. But I have just kept both of them the same momenta k.
Okay. So in general, for instance, in the first line, I'll have just two separate terms with different k1 and k2, for instance.
Yeah. You can have, yeah.
But I think you're assuming that the photon and the graviton both are equally soft. Like one of them is not softer than the other.
Yeah. So to
Is
derive
that important?
Yeah, to get the single soft theorem, it is not important. But if we try to generalize this thing to the multiple soft photon graviton theorem, that would be important. But here also you can think like I am giving even covariantization, I am giving same importance to photon and graviton both. Like otherwise, if one of the momentum is greater than the other, then in the expansion I have a ordering like which whether at the subleading order I will keep fast photon or graviton. But in that way you will only receive the subleading soft photon or subleading soft graviton if you make a momentum like K1 is like if you say photon momentum is K1 and graviton is K2 and you make a ordering.
I think my question was like for a simpler version. I mean, I can take two different Ks, for instance, K1 for a photon and K2 for a graviton,
Right.
and take both of them simultaneously to 0. Keep making sure that the ratio still stays constant.
Right.
So in that case, I'll just have a generic.
Yeah, you will have the same expression with the basically photon K you just replace by K1 and the graviton K you replace by K2. Yeah.
Right.
So I have written. Yes.
I have some question. Maybe I have missed something. So in the first lecture, you are saying the for soft photon only leading order is universal, and
Right.
for graviton up to subleading order is universal.
Right.
So why you are getting both for the soft photon and soft graviton the up to subleading order, the universal part?
No. Actually, there is non-universal piece which is the last line. So you see, I have kept a ni mu nu factor. Okay.
Biswajit, will stop your screen sharing. I think it will help if you just put an arrow like which is which part.
Okay. So yeah. So maybe I should use different color. Okay. So this will be the okay. This color will not be visible, I think. So let me use this color to be the for the photon, and this color for the graviton. Okay. So then you can see that. Let me put tick on this. So this will be the the graviton part will be this term, and the graviton part will be all this term. Oh, is it lacking or frozen?
I think it's lagging. You can continue.
Okay. So this will be the graviton part, and the photon part would be using some kind of color.
It's lagging too much. I think maybe you should just start the screen share again.
Okay. Okay, so here I have given the color things. So you can see the soft photon part as the green parts, which are basically in the first line, the leading soft photon part. And in the second line is basically the universal part of the subleading soft photon theorem. And in the last line is the non-universal piece. I will tell what is this Ni is. And the orange color is basically, you can see the leading soft graviton part in the first line. And in the third line full is basically the subleading soft graviton theorem, and there is no non-universal piece for the subleading soft graviton, which basically depends on kappa or xi or any other information of the theory. But this Ni actually depends on both this C, whatever I define in the as a non-minimal coupling term, and as well as kappa and xi. So just roughly how this N looks like, I will write. So maybe the exact expression I can also write. So this Ni mu nu minus pi has the expression is like I upon 4.
Biswajit?
Yes.
So Akhil has indicated that he actually is red-green colorblind, and he couldn't distinguish between which one is the soft photon and which one is the soft graviton.
Okay, maybe I should then put cross tick.
Yeah, maybe you should just put cross tick.
Okay, sorry.
No,
No, it's
changing
okay.
one of the colors will do. Like
I think just
Okay.
put a cross on the photon, so I think that will be the simplest.
Yeah. I'll do that.
And also, I should indicate that it's already past 12:30, but let's give you 10 more minutes to wrap things up.
So this is the soft photon part. I will use cross, and I will use tick for the soft graviton piece. So the soft photon piece I have crossed, and the soft graviton piece is the rest. Okay. So the right is basically the soft graviton part, and the cross part is basically the soft photon piece.
We have a question from Pranjal Pandey.
Okay.
So he asks, what happens after subleading for photons and sub-subleading for gravitons? Factorization doesn't happen.
Yes, factorization, complete factorization would not happen. You cannot write in terms of the amplitude without soft photon or graviton.
Also, I should say that this was already answered in yesterday's lecture. If you have missed it, you can see it from the YouTube video. And if there are further questions, you can ask in Slack.
Yep. So the N has the expression. This C is basically the non-minimal coupling term which I introduced. And then you have a gamma I of minus pi. So this is the expression. You can see that it depends on the kinetic terms, which kind of particles are there, and it depends on their kinetic term, and also this non-minimal coupling term which I used. So this is the non-universal piece of the soft photon theorem which appears in the subleading order. Now just I want to make, if you try to do the analysis for the soft graviton theorem up to subleading order, you can see that there you can add a term which is like non-minimal weight coupling to the Riemann tensor. In a sense, like if you like, you can, for the graviton case, you can have a term which is like, say, some momentum integrals and delta functions, and you can have a r mu nu rho sigma k phi alpha u1 times some arbitrary non-minimal coupling term, alpha beta, and then mu nu rho sigma some q2 phi beta of q2. Such kind of non-minimal terms you can add, where r mu nu rho sigma k is basically like epsilon mu rho k nu k sigma and all the other terms, right? So this is, you can see the already quadratic in the momenta. So it will affect this kind of vertex with graviton and the one pay vertex gamma 3, and it will make order k square. But now if this kind of vertex is attached to an amplitude and the propagator will give 1 over k, so roughly this contributes to order k. And in the soft graviton theorem, we have seen the leading order is 1 over omega, subleading order is omega, subleading order is omega to the power 0, and sub-subleading order will be omega. So this kind of non-minimal coupling will affect the order omega term, which will appear in the sub-subleading order and makes the sub-subleading soft graviton theorem non-universal. Okay, and also you have to keep all the other covariant terms up to quadratic order in K to analyze the sub-subleading soft graviton theorem. So with this, let me briefly give the, if you try to derive the multiple, so in like I have 5-6 minutes. So if you try to derive the multiple soft graviton theorems, and let me now focus on the soft graviton only. So suppose there is m number of soft gravitons. Right? So how you will analyze? First of all, in a number of soft gravitons, if like you see that if there is some kind of diagrams where all the particles, all the gravitons are connected by 3-point functions, then how many number of propagator in this diagram can have? You will have a m number of such kind of propagators, and each of them can contribute 1 over k. So this kind of diagrams will contribute 1 over omega to the power m if there are m number of gravitons are connected by vertices all are gamma 3, right? So this will be the leading contribution 1 over omega to the power n, and in the subleading order you will expect the contribution will be 1 over omega to the power m minus 1, the next term. And if you try to analyze only up to the subleading order, then you only have, first of all, you only have to keep like the linear, like only the linear in derivative of the momentum term in the covariantization procedure.
Biswajit, your screen has once again stopped showing.
Oh. So,
Or no?
Yeah.
I think for the last 5 minutes, maybe you can share the screen and Biswajit can write on his iPad. I think that will be best.
Yeah. Biswajit, can you stop sharing?
yeah. And stop still.
Okay, Biswajit, continue.
Okay. So, yep. So basically what I was telling is that like if there are m number of soft gravitons, how to do with the leading order diagram, like contribution to the leading order, which kind of diagrams contributes. You can see if all of the m of the soft graviton is connected to the vertex gamma 3, then there will be m number of such kind of propagators, and each of the propagators will give a 1 over omega factor. So the leading order contribution you will get like 1 over omega to the power m minus 1, right? Now, like now in the subleading order, you can allow only the terms which are basically 1 over omega to the power m, and the subleading order is 1 over omega to the power m minus 1. So in the subleading order, you can allow only this kind of diagrams, which basically can give a at least one momenta less leading to the leading kind of diagram. So what kind of diagrams those can be? Suppose all of them are gamma 3 and one of them is gamma 4, where two gravitons are connected to the finite energy particles via same vertex, 4-point vertex. So you see, due to this reason, what happens is that one propagator becomes less, right? Because now since two of the gravitons connected to a single vertex gamma 4, so now you will have a m minus 1 number of propagator for this diagram. Propagators. So this obviously contributes to 1 over omega to the power m minus 1. Right? Now you can have other kind of diagrams, where basically
Arnab, switch to next slide.
Where you can have other kind of diagrams, where you can see, suppose all the other gravitons are connected to 3-point vertices, but one of the graviton is like two of the gravitons is connected by a 3 graviton vertex, and one graviton propagator, and that connects to the gamma 3. So obviously what happens is that due to, since two of the gravitons connected via single gamma 3, so one propagator decreases, so it again have a m minus 1 number of finite energy propagators. So that gives 1 over omega to the power m minus 1. But you may think that, but there is a graviton propagator involved here. Like suppose this is kr, this is ks. So you will have a kr plus ks. So that can give 1 over kr plus ks whole square. So that can give you 1 over kr dot ks term, right? So this propagator can give you 1 over kr dot ks term. But you see this graviton, 3 graviton vertex also coming from square root g r term of the soft graviton, right? And that involves also 2 derivative. So that has 2 factor of k, and this basically again cancels the effect extra, like 1 over omega square effect of this thing. So again, this kind of diagram also contributed 1 over omega to the power m minus 1 overall. So contributes to the subleading order. Now you can say that is it enough that only 3 graviton vertex would be enough, or you need more graviton vertex, like 4 graviton, 5 graviton vertex, all that. But one can show that actually all the other like vertices will not contribute, only the information one needs. So let me give an example of that. Suppose you consider a 4 graviton vertex, right? So first of all, for that already, since 3 of the gravitons connected to a single by a single gamma 3, already you are decreased by compared to the leading diagram. Now you have a total m minus 2 number of finite energy propagators, right? So that gives 1 over omega to the power m minus 2. Now you can think that, okay, I have a graviton propagator, whether this will help, but this will also not help, because like suppose this gives 1 over omega square part from this propagator. So I am calling all the gravitons to be basically soft, like all of them the energy omega and some different directions. And then this will give you 1 over omega, but this vertex, 4 graviton vertex also will give a 2 factor of k momentum of the particle. So this will omega to order omega to the power 0. So that kind of diagram contributes 1 over omega to the power m minus 2, which goes to the subleading order. And if you are only interested to the subleading order, you don't have to bother about contribution from the 4 graviton vertex and so on. So the only information to derive the multiple soft graviton theorem you need the information about the vertex gamma 3. You need the information about the vertex gamma 4, where basically 2 of the gravitons connected to 2 finite energy particles, and also kind of the diagram involving the vertex gamma 3 and a 3 graviton vertex. So if you try to draw with all these vertex, all possible diagrams, and sum over the contribution, you will get a multiple soft graviton theorem. Okay, so is there any statement question I can take at this moment? Otherwise, I will write down the expression for multiple soft graviton theorem.
Biswajit, you are already 2 minutes over your 10 minutes overtime, and okay, writing that expression, I know personally, will take 2-3 minutes more.
Okay, maybe in the next lecture.
Yeah, so I think it was a bit too hurried. So if people have any pressing question, please ask now, or otherwise we will stop the recording and people can ask more informal questions over the Zoom.
Is there any question?
Okay, I guess there are no pressing questions. Then let me pause the recording, and till 1:10 people can ask questions to Biswajit about this lecture. Just to remind you that he's going to also give the last lecture of today. Okay, so welcome back to the post-lunch session of day 2 of ST4. So before we begin with the lectures, I just want to draw your attention to a poll that is there in the Slack in the channel Break Room Banter. So it's a poll targeted towards especially the younger PhD students. The speakers as well as the organizers have noticed that the younger demographic are not asking too many questions or participating in the discussions. There can be a variety of reasons for that, but we feel that if you have a separate discussion session or a dedicated discussion sessions with the speakers, because both of our first speakers will be finishing half of their lecture course after today, 3 lectures each. So it might be a good idea to sit with them separately and have a discussion. So if you want that, please respond to that poll so that we can set it up accordingly. So with that, Subbu will start his 3rd lecture on supergravity. Over to you, Subbu.
Yeah, thanks. Hi. So I'll begin with a recap of what we have done so far, so that we have a view of what is happening from above. So we defined, so we studied Clifford algebra in 4 dimensions, right, which satisfies this relation. Okay. And if we have representations of Clifford algebra, we have representations of Lorentz algebra. Okay. And using this, we defined a spinner. Okay. So spinner would be something that transforms under Lorentz transformation in the following way: lambda gamma by 4 psi. Okay. Where basically gamma mu, this is gamma mu nu by 2, where gamma mu nu is the antisymmetric combination of the gammas, and another half factor for the normalization to avoid overcounting. Okay, so this is how we defined a spinner, and initially it was a complex spinner with 4 components. We asked, can we give a condition, can we impose a condition on the spinner to reduce the number of components so that we have the simplest spinner in 4 dimensions. Okay, and whatever that condition is, it must be compatible with this transformation rule. Okay, so in order to do this, we needed to introduce an important concept called Majorana conjugate. Which is called, we defined this way, where this matrix is called the charge conjugation matrix. Okay, and it's not unique. There are 2 such matrices for any given representation in 4 dimensions or in any even dimensions. Okay, and it has this property. In the complete Clifford algebra that we defined, every matrix is either symmetric or antisymmetric. Okay. Now, what was important was that this psi bar transforms the same way under Lorentz transformations as I psi dagger gamma 0. Okay. So that told us that if we equate the 2, that would be a Lorentz invariant condition. Okay. So psi bar is equal to I psi dagger gamma 0 is a Lorentz invariant condition. Okay. And so this condition is called as the Majorana condition, along with T1 is equal to -1. Okay. That was needed because if we impose this condition, then we are relating the complex conjugate of a spinner to itself, and complex conjugate of the complex conjugate should give back the spinner, okay, which forced us to say that T1 must be -1. Okay, and it's easy to see from here, this contains transpose of psi, this contains dagger of psi. Therefore, the full relation, when you manipulate it, it should relate a spinner to its complex conjugate. So this tells us that there must be a way in which we can write this relation so that it is clear that it is related to charge conjugation, because whenever you have complex conjugation of a spinner, it takes you from the particles to the antiparticles, right? So that we could do by using this. So this is also an alternate form of Majorana condition. Okay. Now here I made a sign error in between the lecture. I got confused, but it was correct in the notes. So if you do I gamma 0, I psi dagger gamma 0 dagger, you get psi. Okay. So I had another minus sign here. Okay, which is fixed in the slides that I've shared in Slack. Okay. So basically gamma 0 square is -1. So this we missed last time. So with all that, there was another minus sign here with psi c, that goes away. So this process is called, so this spinner is called charge conjugated spinner. Okay. And the fact that the spinner is equal to the charge conjugate implies that for a Majorana spinner, the particle is its own antiparticle. Okay. So that is the idea. And we studied 2 important properties of spinners. One is Majorana flip, okay, and another is fierce identity. I won't write them. Okay. But we realize that if we use both of them, then we can manipulate any expression that involves spinor to a simpler form. And this we will see today when we prove the Susy invariance of superangles. And then we went to supersymmetry and we considered Susy algebra and we studied massless supersymmetry representation. Okay. So I will cover later on why massive representations are not so important for these lectures. Okay. So we studied massless Susy representations, except I made one error, which is why we got a multiplet twice. Okay, which is that when I began with n is equal to 1, I took our h0 to be 0. Remember, h0 is we defined the vacuum for the Clifford algebra, raising and lowering operators, or Q dagger raising and lowering operators. Okay, and then we applied Q dagger J. Okay, and this decreased the helicity. And the CPT conjugate sector had K bar minus H0. Okay, and we applied with QJ, and this increased the helicity by half. Okay. What all of this means is that if H0 is positive, right, then H0 is the maximum helicity. Okay. So therefore, when I was taking H0 is equal to 0, I was taking that H0 is equal to 0 is the maximum helicity, but that's redundant, because even if you take H0 is equal to half as the maximum helicity, right, you get half decreases to 0, okay, and then you get the same multiplet. So I should have really started with H0 is equal to half. Okay. So apart from this subtlety, everything that we did was correct. Okay.
Can you repeat that again?
Oh, okay. Yeah. So what I mean is, let me go to this slide. Yeah. So when I considered these representations, I began with H0 is equal to 0 and lowered it to get minus half. Okay. And then I again took H0 is equal to minus H0 is equal to 0 in the CPT conjugate sector and raised it to plus half. Okay. But the point is that when we say something is maximum helicity, okay, might as well start with half, because if you start with 0, right, 0 went to minus half, and then again 0 went to plus half when you raise it. But half will also do the same thing. If you lower half to 0, okay, then you have 1 half and 1 0. In the CPT conjugate sector, you have minus half and you raise it to 0. So you have 2 zeros and 1 spin half, which is the same in both these cases. So if you want, you can do both of them. It's just that you get the same multiplet. Is that okay?
Yes.
Okay. Yeah. Okay. Right. So apart from yeah, sure.
Did you ever call one of this starting state a vacuum, or did you not?
Yeah, it is vacuum for this algebra, but in a particular sense, in the sense that
it's just the lowest weight or that kind of statement.
Yeah, in the sense that, okay, so maybe I did not define the vacuum condition. So Qj annihilates K bar H0. So that was the vacuum condition. And then Q dagger J, Q dagger J gives it additional indices, which we had somewhere.
Yeah, lowers the helicity.
Yeah, these indices, right? These I1 to IM indices. So these indices came because we acted with Q dagger. But if you acted with Q, then this state would have been annihilated. If you acted with
but
Q,
you haven't shown it's a vacuum in the sense of lowest energy or something. No? That
it is not. It is not a vacuum in. I mean, okay. I don't want to say it's a vacuum in that sense, right? I mean, we just have the operators action on these states. Okay.
Yeah.
And we see that they act as creation and annihilation operators. Okay. And now we are asking, in massless representations, we already know there is the structure K bar H naught, right? So now we are asking if we, and this is the action over that, in fact, right? So this and this action, right, is over that, because J3 came up because we were considering K bar, which has K00 K. Okay. So for that state, okay, this algebra acts in this way. Okay. And the action of the algebra tells you that one of these can be a creation operator and the other, one of these is a creation operator and the other is an annihilation operator. Okay. And the Hermitian.
Can I make a?
Yeah.
Can I make a comment on that?
Anish,
Yeah,
I think Nishant had his hand raised. So.
No,
I see. Okay,
if he's making a comment on the same thing, then let him continue.
Yeah, so
the way I would say this is that you have, you usually have, you have the existing Poincare algebra, and usually you have the Casimirs of it are the mass and the Poly-Lubansky vector.
Right.
But in supersymmetry, Poly-Lubansky vector is no longer a Casimir, so you cannot have particles of definite spin in that in that sense. So you have your usual Fock space where you build a state. But for a given momentum, you don't have particles of definite spin. So within a given momentum value, you have this additional algebra where you can create states. So that's what, I don't know if that makes it clearer.
No, I think Poly-Lubansky vector, for massless particles, is it needed? As far as I know, a massless particle has two helicities, and that does not change in supersymmetry.
Yeah, but the Poly-Lubansky vectors actually gives the helicities for the massless vectors, no?
As far as I know, is it for the massless vectors?
Yeah. For the massless, the Poly-Lubansky gives helicity, and for the massive, it gives the spins.
No, that might be a naive way of saying it, but like representation theory, if you do it carefully, massless representations form this ISO2. So even though helicity looks like P dot J, okay, which would also generalize to Poly-Lubansky, operators. But if you do it carefully, then I think massless representations, they have two helicities. I don't know. Maybe we can discuss later.
Yeah, they do have two helicities, and they are indeed the eigenstates of the Poly-Lubansky vector. The definition of the Poly-Lubansky vector has nothing to do with massive or massless. The fact that that's a Casimir is independent of whether you're talking about the massive representation or the massless representations of the group.
I see.
Right.
That is possible. Okay.
Yeah.
I am more familiar with the way that Weinberg does it, for example, and I don't think that analysis changes with supersymmetry.
Yeah, the analysis doesn't change. That's correct.
Yeah.
So Nishant, please go ahead. You have your hand raised for a long time.
Yeah.
Okay, thank you. So I have one question regarding the this notation.
Yeah.
So this the commutator, this anti-commutator that you have on slide 26, this current slide.
Yeah.
So this you got in wild representation, right? So this is when you consider the left-handed chirality of the commutators.
Yeah.
So similarly, so they correspond to this QI1 and QI2 are the two supercharges.
Yeah.
So similarly, there will be two more supercharges for right-handed chirality sector also, right?
Yeah, they will come in the CPT conjugate sector. Yeah.
Oh, so they correspond to the CPT conjugate.
Yeah.
Okay. All right. Okay, thanks.
Okay.
I have another question. It might be a bit tangent to the topic, but
Sure. Yeah.
So one often hears this kind of statements like in Euclidean signature, the number of spinners get doubled. For instance, when you talk about the gravity multiplet, they say that in Euclidean signature, the number of spinners are doubled. Can you just say what does that mean, or why is it so?
Oh, actually, I don't know anything about it. We could discuss on Slack though, if you provide some reference.
Dipanshu, go ahead.
Yeah, Debbie.
So this is also a bit maybe because you said that you are going to work only in 4D. So So yesterday you identified n number, like you have associated 4 supercharges with n equal to 1, where these are coming from Majorana spinners. So if you are in d equal to 3, where there are no Majorana spinners, then in that case, how do you exactly count number of supercharges? Say d equal to 3 example.
Yeah, so in any dimension, you look for the minimal spinner in that dimension.
Okay.
So in some dimensions, what happens is that there are these Majorana Weyl spinners. I think that's the case with 3 dimensions.
Okay.
And also with 6 dimensions. So there, Majorana Weyl means that, I mean, I did not cover it, but you can show that Majorana condition in that we have here, right? In 4 dimensions, it is not compatible with Weyl condition in the sense that you could ask, can a Weyl spinner satisfy this condition? That would further reduce the number of components, right? But that is not compatible in 4 dimensions, whereas in 6 dimensions and 3 dimensions, they are compatible, okay? So whenever they're compatible, you have this n comma m kind of notation, nl comma nr if you wish, okay?
Yes.
Where, yeah, so that, so, but ultimately, if you want like a more, general notation, then people just, expand out the number of components and say n is equal to 1 SUSI has 4 supercharges. And for example, I know that 5-dimensional n is equal to 1 supergravity has 8 supercharges, which is the same as n is equal to 2 supersymmetry in 4 dimensions. So that is the language that is used.
I see. Thank you.
Yeah, many people have raised hand. Yeah.
Ashwin first.
Hello. I want to ask you that. So yesterday, I think you mentioned in four dimensions you can have up to, maximum n equal to 8 supersymmetry. This corresponds to supergravity.
Yeah.
But isn't this statement true even for the general dimensions?
Yeah, so in general dimensions, that is not the notation that is used. N is equal to 8, as we discussed, is specific to 4 dimensions, the notation of the language. But if you say the supersymmetry with 32 supercharges, okay, that is the maximal supersymmetry in any dimensions. And that follows from this Lavendi argument that I explained to Lata.
Okay.
Mrityunjay?
Yes, so I think this Majorana Weyl condition is possible only in 2 and 10 dimension.
Sorry?
This Majorana Weyl condition is possible only in 2 and 10 dimension.
Okay, maybe.
I think 2 mod 8 is the correct.
Yeah, 2 mod 8.
I see. Yeah, that is okay. No, I was just saying, like, I didn't mean to, establish that 3D has it. I was just saying that it is possible.
Neetu, go ahead.
I just wanted to make a comment regarding Debbie's question, but I think somebody has already said it in chat that Majorana spinners do exist in 3 dimensions. Yeah, I just wanted to say this.
Yeah. Okay, I also checked, like in this book, that in 3 dimensions the minimal spinner is Majorana spinner. Yeah. Thank you. But yeah, I mean, with the techniques given, you can find it in any dimension.
Sorry. I said something wrong about 3D specifically. My question was about in general in some dimension where I'm not allowed to have Majorana.
Yeah, basically whatever I answered you is the answer. I mean, we are just debating about like what is the precise thing in 3 dimensions. Yeah. Okay. So, right. So we discussed representations of supersymmetry. Okay. And one thing that I didn't mention yesterday, which is that for n is equal to 3 supersymmetry in 4D, I mean, of course, everything is happening in 4D so far. Okay. If you have multiplets, okay, multiplet is a collection of fields which forms a representation of supersymmetry. That is the language. Okay. So whatever collection we had, like of some spin and for each h0 value, that is called as a multiplet when you represent in terms of fields or. So multiplet which have spin less than 2. Okay, no particle should have spin 2 or higher. Okay, so then they also have n is equal to 4 supersymmetry. Okay, so you can see it by taking the multiplet and adding its CPT conjugate, and you will see that once you add the CPT conjugate, then you get the same number of degrees of freedom as the corresponding n is equal to 4 multiplet. Okay, so for example, n is equal to 3 vector multiplet also has n is equal to 4 supersymmetry. Like you could construct an n is equal to 3 super Yang-Mills Lagrangian, okay, but then once you compute its currents, you will see that by some field redefinitions, it will also have n is equal to 4 supersymmetry. But this is not true for supergravity. Okay. So if you look at the number of degrees of freedom for n is equal to 3 and n is equal to 4 supergravity multiplets, they are different. Okay, and they are given in the notes, so you can check. And later we will discuss some more details about n is equal to 3 supergravity. Okay? Not much, but just some new developments. Yeah. So today we will discuss using this HLS theorem that I briefly stated yesterday. Okay? Haag, Lopusansky. Okay, there are some accents here which I don't really know, so I'm just writing usual alphabets. So, okay, so HLS theorem.
So disrespectful.
Sorry?
I just said so disrespectful.
yeah, sorry. So, HLS theorem. Okay, so it says that if you have any relativistic quantum field theory which satisfies the same assumptions as Coleman-Mandela theorem, okay, then if you have, let's say, some n conserved spinor charges, it implies the theory has n extended supersymmetry. Okay, this is the only allowed graded Lie algebra that involves both commutators and anti-commutators, consistent with these assumptions. Okay, so assumptions such as below a mass there should be a finite number of particles and so on. Okay, so and also note that yesterday also I made this argument that if you have a spinor charge, okay, it is necessarily coupled to it will necessarily have a non-trivial commutation with the Poincare algebra, because any spinor charge delta q under Lorentz transformation will go as lambda dot gamma by 4q. Okay, so this implies that m comma q is not equal to 0. Okay, because it is from the commutator. Yeah.
So this is regarding the first statement that you made, that if we have n equal to 3 CP multiplex, then we also have n equal to 4 supersymmetric. So is this statement about the same dimension or different dimensions? So, like n equal to 3 Susi and n equal to 4 Susi, they are in same dimension.
4 dimensions, yeah. Both are in 4 dimensions.
Okay.
It's like some supersymmetries are in the sense that suppose you try to construct a theory with only n is equal to 3 supersymmetry, you would have constructed a theory with n is equal to 4 supersymmetry, which was not your purpose, or you may not have noticed. But once you compute the currents and do a field redefinition, you will see that there is one more conserved current.
Okay.
Subbu, are you there? Okay, I think there is some network issue from Subbu.
He's back in the keynote, so probably he will be back in.
Yeah, hopefully.
Yeah, hi.
Hi, Subbu.
Ouch, sorry. 1 second, it will soon start. Oh, yeah. It has started broadcasting, but somehow I can't see it.
We can see.
Yeah. Okay. There was a lag, I guess. Yeah. Yeah. Okay. So Neetu, is that clear?
Yeah.
Okay. Yeah. Okay. So today we will use this HLS.
What was the statement about the n extended supersymmetry? I missed that. Sorry.
Oh, n extended just means that this Qi are n in number, the supercharges.
Oh, okay.
So what I mean is, suppose there are 4 conserved spinor charges, like Marana spinor charges. Okay.
Okay.
Then that means 4 n is equal to 4 supersymmetry.
Okay.
Yeah.
Thanks.
Yeah. I wanted to ask something.
Yeah.
Last day's lecture, you mentioned that this Helicity 3/2 thing is inconsistent. Like, could you or someone else give a slightly clearer argument why is that so?
Yeah, Helicity 1 and multiplied with Helicity 1 and Helicity 3/2.
They are both disallowed, not allowed, right?
Yeah, I mean spin 3/2 is Helicity 3/2 is allowed, but only with a Helicity 2 particle, like in the gravity multiplet.
Yeah, without Helicity 2, what is the issue with it? Could you?
No, with Helicity 2 it is fine. It is a supergravity multiplet. But with Helicity 1, you won't have a consistent interaction term that you can write down.
Yeah,
but
so
I don't know much.
Yeah,
I don't know much more about it. What I know is that, like if you have a Helicity 3/2 particle, which is massless, okay. One thing I know to write down is a gravity no, which is a spinor gauge field, okay. Psi mu alpha, okay. It has both Lorentz index, okay, and spinor index. I'm sorry for using like the same kind of letters. So now the point is that if you consider such a gauge field, okay, to be producing your massless spin 3/2 particle.
First of all, why should it be a gauge field again?
Because it's a massless particle. So, I mean, this is the only way I know to construct a massless spin 3/2 Helicity 3/2 field. So what I'm saying is this is how I understand it, but I don't know like if there is a rigorous way to show that this is the only field that is there. But if you consider this field, right, then the corresponding charge associated with this field will satisfy supersymmetry algebra because it is ultimately a spinor, symmetry. Okay, and if it satisfies this supersymmetry algebra, then since Q closes to P, right?
Mm-hmm.
So, and P is translations, right? If Q are made local, right, which is the case here because sin mu alpha is a gauge field, right? Then P must also be made local. And local translations are general coordinate transformations. So, you should have the graviton also. So, unless you have the graviton, a spin 3/2 field with a spin 1 field is inconsistent. This is how I understand it. But I don't know like if there is a more general way of saying like why this should be the spin 3/2.
Like, should I understand this Rarita Shunya kind of Lagrangian are all inconsistent outside supergravity? Is that a valid conclusion?
Okay.
Like
sorry,
just a Q of T of Rarita Shunya fermions. Is that inconsistent?
Yeah.
Without gravity, of course.
Yeah, I think the free theory is consistent, but if you try to couple it to something, then.
Yeah, I think the free theory you can treat just like by itself, but if you try to couple it to gravity, I suppose there are
not gravity. I mean, without gravity is the issue, right? You're saying you can't have an interacting theory of Rarita-Schunger fermions. Is that what I should understand from the discussion?
Yeah.
So,
yes.
if you try to include an interaction of anything which is spin greater than 1, then for massless tests, then Weinberg-Witten theorem says that you must include gravity. So otherwise, you cannot have you need something which couples to the stress tensor. So that means gravity.
So you're saying this discussion follows from Weinberg-Witten theorem, right?
I mean that's one way to argue that. There might be other way to argue also. So if you don't include gravity and try to write down interaction terms of spin 3/2, then you will never succeed. I mean, it will lead to some pathological quantum field theory, interacting quantum field theory.
Okay, I'm facing like new kind of problems here. Okay, which is.
Subbu, we can't see your iPad screen.
Yeah, that's what. So somehow it is saying like connect. Can you? One second. I have to resort to this because it is saying.
So would you prefer that if one of us shares it and you continue doing the lecture like Biswajit did for last 10 minutes?
Oh, yeah, maybe, I don't know. So what is happening here? One second.
Sure.
Yeah, okay. Yeah, maybe let's try this and then we can try back
sure.
iPad through my iPad, and if nothing works, we can go back to it.
Sure, go on.
Okay. So Akhil, were you happy? Like, I mean, this is what I know. We can discuss more in, let's say, Slack.
Yeah, thank you.
Okay. Yeah. So now what we will do today is using HLS theorem, we will prove Soucy invariance of n is equal to 1 super angles. Okay. So n is equal to 1 super angles multiplet is just the vector multiplet which I described earlier. Okay. I see there is a huge lag. So vector multiplet which I described earlier, but taken in the adjoint representation. Okay, so there is a field A and a field lambda A. These are adjoint indices. Okay. So now, so this is the multiplet that I said earlier. Okay, this is spin 1. This is spin half, and both are massless particles, so it's really helicity. Okay, and we consider the gauge field to be in some adjoint. Gauge field is not in the adjoint representation, but what I mean is that we consider gauge field of a compact group, and these are the structure constants. Okay. And because the group is compact, okay, FBCA is completely antisymmetric. Okay, in all the three indices. This we will use later. Okay, and we have the fermion, and the fermion I will write the covariant derivative plus 3 Okay, Subramanya, do you guys also have the delay, or is it just me?
There is a delay.
Okay. I see. Yeah. So this is the transformation of the gauge field. Okay, and then there is a covariant derivative. Okay, I'm not very happy with this actually. Let me try joining from my iPad for one last time.
Okay, sure.
It says attempted to start an invalid broadcast session. And it also asked me that it will stop someone else's screen sharing.
Subbu, I don't see you in the list of participants, the iPad version of you.
Oh, but I see it.
No, Subbu iPad is there, no?
Yeah. Okay, yeah, now it's working. Oh, it has failed to start. Okay. Yeah, I don't.
Can you try sort of leaving the meeting from your iPad and joining again?
Oh, yeah, that would be good. Yeah. Yeah, can you just tell me the password and the meeting ID?
Yeah, just a second.
Meeting ID is 813
813
7195
719555. Yeah.
20. Password you need it?
Yeah, 1 second. Yeah, now I need the password. Yeah.
705
705
423.
So it might also be a good idea to turn off your video.
Oh, yeah, I can do that. Okay, just make me co-host. And
Yeah, I will do that. It's just your iPad is taking a long time to join.
Yeah, it is taking a long time. Maybe I need to change the Wi-Fi. 1 second.
Okay, you're a co-host now on your iPad.
Okay. Okay.
Great.
Yeah. Okay. So this is the covariant derivative of the spin half field, and the action ST4. I mean, these things above, I am assuming everyone knows because this follows from classical field theory. But of course, I mean, please ask questions. Then people can explain if you missed something. So this action, okay, where this is the covariant derivative that was defined here, okay, this implies the following equations, where the first equation is not really imposed by the action, but it's the Bianchi identity, okay, and these are the equations of motion, the next two equations, okay, and d mu f mu nu, sorry, f mu nu a, okay, is equal to minus g by 2 f bc a lambda bar b gamma nu lambda c. Okay, so these are the equations. Okay, and I think people can derive it. Okay, so let me just copy it to the next slide. But if there are any questions, I can answer. Okay, so this is the setup of n is equal to 1 superangles, where we have just taken a vector field interacting with the spin half fermion, and these are the equations of motion. Okay. And we are studying them because we want to show that there is a conserved current, and we'll just propose a conserved current, okay, because we want to save time. Okay, and also let us say, using these equations, we will be able to guess that this is the conserved current if we know enough about spinors and so on. Okay, F mu rho A B gamma mu. Okay, so this is the current, and what we will see is that this current is conserved, and that will tell us that n is equal to 1 superangles has supersymmetry. Okay, is that clear? Okay, so now of course this current has no gauge indices, okay, under this compact.
Sorry.
Yeah.
In the equation above, so d mu. Oh, okay. Sorry. Yeah. No.
Oh, sorry. I think I missed many things. One second. What have I done? Gamma mu lambda A. Oh, I think this lambda bar B is not there. So, okay. So this was my conserved current. Okay. Yeah. So now what we need to show is that this current is conserved.
Can I ask something?
Yeah.
Like the current is fermionic or?
Yeah. Because this is a fermion, right? This is a fermion.
Yeah. It's like since I'm just not used to these kind of things, like if a current is fermionic, does it mean I can measure it, or like what does it mean? Like
no, you can't. I mean, well, okay. I mean, okay. Conserved fermionic charges you can't measure, like I think in the classical sense. Okay, but it plays the role that if you have that conserved charge, then that generates a symmetry which relates some amplitude to some other amplitude that you need.
I think bilinears of this fermionic currents should be observable or measurable.
Yeah. Okay, that's a good point. Yeah.
Also the zeroth component is none of the superchargers, no? Just
zeroth component is if you integrate it over space, it will be the charge.
Oh, okay.
Supercharge.
Okay.
Yeah, in the usual way, in the Noether prescription way.
Okay.
Wait, hold on. Are we talking about observation?
Yes.
Yeah.
In a purely supersymmetric theory.
This is starting to worry me greatly, but okay, I won't say anything.
We are amidst pandemic. We are dared to dream.
Sorry, Subbu, I'm just going to like keep interrupting with bullshit like this because I need to lighten the mood. I feel like people are not really talking, so maybe my nonsense will help. I hope.
Yeah, I like how you have found a way to justify it, but all right. Yeah. Okay. So let me continue. I mean, I have no issues with it. Okay. So let's see that this is conserved. Okay. So now this whatever we have in this J mu, this does not have any SUN indices, right? So that tells us that the partial derivative on these objects is in fact the covariant derivative. Okay. And we will see that this is, when you use the product rule, only this term will survive. Okay, because the second term is proportional to d slash lambda a, right? Because this gamma mu d mu will act on lambda a, right? And that will give us d slash lambda a. And by equation of motion here, which is gamma mu d mu lambda a is 0, this is 0. So currents are of course conserved under equations of motion. Okay, and then we further need the relation that we need gamma nu rho gamma mu is equal to gamma nu rho mu minus 2 eta mu. Okay, this I leave as an exercise with a hint. Okay, and the hint is that use gamma nu rho mu. Okay, I mean, I'm just writing it to make something clear. It's obviously antisymmetric. Okay. That is gamma nu rho. Okay, so use this. Okay, if you don't understand why this is correct, spend some time on it. We have explained enough to understand this equation. Okay, and then using that derive this relation. Okay, that is the exercise, and I think it's useful. Okay, so if you do this exercise, then this expression becomes del mu j mu is equal to gamma nu rho mu d mu f nu rho a, okay, minus 2 d mu f mu nu lambda. Now, if you see this first term, okay, the first term will vanish, okay, because if this is antisymmetric, if gamma nu rho mu is antisymmetric in all the three indices, which it is, okay, then this must also be antisymmetric. Okay, so that by Bianchi identity that we have written here for the gauge field, okay, this will go to 0. Okay. So the only non-trivial term that we have is this. Okay. Okay. So maybe I can give some time for people to write.
I have a question.
Yeah.
So, is there a way to derive this J mu from some first principle or something like that?
Yeah.
So, how do you derive this thing?
I mean, okay. How do you derive it using usual Noether procedure? Okay. For example, I mean, for that, what you need is that you need the transformation of these fields. Okay, like what I have not given to you is that I have just said that this action is supersymmetric, but I have not given the supersymmetric transformations, right? So if you knew the transformations, then using the transformation rules, you can find the current. And to obtain the transformation rule, you know what are the fields in this multiplet by massless Susy representation theory. Okay, so then what you basically need to do is just say if left hand side is, let's say, delta A mu A, by symmetry what are the things that I can form on the right hand side. Okay, and then demand that it is consistent with supersymmetry algebra. That will give you the transformation rule. And once you have the transformation rule, using Noether's theorem, you can find the super currents. Okay, but to save time, and because I don't want to go into a course on supersymmetry, what I did is use this approach. It's also used in Van Proyen to introduce Susy for the first time. Okay, so I just gave you the action and proposed the supercurrent and said that I'm showing that it is conserved.
Okay, and one more thing. So when I look at this action, this is like some generic action for some non-abelian gauge theory, right?
Yeah.
So by looking at action, from action I cannot tell like whether this is a supersymmetric action or like some normal action. So like even if you have like a quantum chromodynamics action, right? So so I mean you have to tell me that this is a supersymmetric action rather than I cannot like guess this by looking at this action, right?
Yeah, I mean in QCD what happens is that I think the fermions are all massive, right? So here both the gauge field and fermion are massless.
Okay.
I mean, in QCD, I think even the gauge, in QCD, yeah. In QCD, the gauge field is massless, but the fermions are massive. But in this weak interactions, like the gauge fields are massive, but fermions don't necessarily have the same mass. And gauge fields are also massive, not because of the action, but because of spontaneous symmetry breaking. So,
okay.
Yeah. So if you have two fields in the same mass, then you begin to ask these questions.
Okay, so they both need to be massless in order to raise a question of supersymmetry.
They can both be massive also, but they need to have the same mass. We did not discuss massive representations, but yeah.
Okay.
Yeah, Arnab. Yeah.
Hi. I'm not very familiar with this supersymmetry. So for n equal to 1 supersymmetry, can you have other multiplet like spin half and scalar?
Yeah. We discussed this earlier, right? Like we made a list, right? So there was this vector multiplet, okay? And n is equal to 1 super Yang-Mills is basically this vector multiplet taken in the adjoint representation of some non-abelian gauge.
Okay.
And of course we had this other multiplet which has like scalars and spin half. Okay, so that is also there. Yeah.
So, and with that you can have another action.
Yeah.
I see. And how do you know that the action that you have written down is the vector multiplet? That is the only thing that you can write down and cannot be anything.
By this massless representation theory, right? The only action which contains a massless gauge field for us was an action which involves the spin half. I mean, okay. What I mean is that you can just begin by this, right? Like you ask, like, okay, I had the vector multiplet. Let me give adjoint indices. What are the fields in the theory? Then these are the fields. Basically, I will describe soon that these are called as on-shell fields. Okay. I mean, fields are off-shell, but these multiplets are on-shell multiplets. So for these, the field content is just given by what we did earlier, the representation theory. So once you do the representation theory, for each of those representations, you ask what are the fields, what is the action.
Okay. And
okay?
so, yeah, and one last thing, like, can you also have an action which contains both these multiplets?
Yeah, yeah. We can couple the matter multiplet to Super-Yang-Mills multiplet. That also we can.
Yeah, what I mean is that can you have an action which has this vector multiplet as well as this spin half and this 0?
Yeah. You can make them interact. Yeah.
Okay. Thank you.
Yeah.
I have a question. We like in earlier slides you mentioned that n equals to 2 supersymmetry will also have a vector multiplet, right?
Yeah.
So if, how would this action change if we are considering n equals to 2 supersymmetry? Like, will there be any change, or the current will change in that n equals to 2 supersymmetry?
Yeah. For example, in n is equal to 2 supersymmetry, there must also be 2 scalars.
Okay. Yeah.
And also the fermion will be a doublet of fermions. Instead of just one fermion for each A, you will have a doublet of fermions. Okay, doublet meaning lambda will have another index I running from 1 to 2.
Subbu, if
Subbu, do you mind if I just make a comment?
Okay, Madhu, go ahead.
Sorry, Subramanya, go ahead.
Yeah, I was just trying to add comment to Subbu's answer to Nishant's first question, that rather than saying that the mass of the boson and fermion are same as a diagnostic of supersymmetry, I think the more powerful diagnostics is the on-shell degrees of freedom of the bosonic fields and the fermionic fields must be same. After all, I can take a different degrees number of bosons and different number of fermions, and I can fine-tune their mass to be same, but there need not be supersymmetry. But if their on-shell degrees of freedom are exactly same and their masses are exactly same, then it's guaranteed that they must have some supersymmetry.
Yeah. I just meant you can begin asking that question.
I don't know.
But yeah.
I'm sorry, is that true?
Sorry?
I mean, like, I'm just like ensuring that the number of degrees of freedom on the boson and fermion side match. I don't think that's sufficient, right?
Yeah, sorry. I mean, what I mean is that it's a more powerful diagnostic than just saying that the bosons and the fermions have same mass. If the degrees of freedom also match and if they have same mass, there is a good chance that they will have some supersymmetry.
Actually, like, supersymmetry is extremely restrictive in the sense that suppose you want like all the other fields that you already have in the standard model, right? And then you want supersymmetry and you want some fields at the same mass. Okay, then you will see that there are only a few choices, and that will
it will restrict the coupling spaces.
So
and everything.
So that is why. So all that I said and Subramanya said are just necessary conditions. They are not sufficient conditions. Yeah. So Madhu, you had some comment.
No, I just wanted to say, because someone was asking about like n equals 2.
Yeah.
So one of the this is generally kind of well known in the supersymmetry sort of community that, like, you can build actions out of some basic building blocks, and you can sort of couple them in various ways. And in order to, let's say, start off with the n equals 1 multiplets and then construct an action that has an n equals 2 supersymmetry, you have to keep various things in mind. So, for example, just elaborating on something that Subbu pointed out, you have two fermions, but now the two fermions are in an R symmetry doublet, right? Because n equals 2 means you have two supercharges and they rotate into each other.
Madhu, I'll discuss all these things later. So I'll discuss all these things later. So maybe we can discuss then. Is that okay?
Sure. Okay.
Yeah,
no problem.
We will discuss in great detail about n is equal to 2 supersymmetry. Okay.
Yeah. Cool.
Okay. Yeah. So now we are left with this this term, right? This d mu f mu nu gamma nu lambda a, right? And this we know from the equation of motion that it is related to a bilinear in lambdas. Okay, so we are left with, okay, I'll just write this thing, okay, which is the, sorry, we are just left with this expression lambda A lambdas. Okay, so where this bilinear, this came from the equation of motion. Okay, this G FBCA and this thing. Okay, so up to proportionality, this is what we have. Okay, so now I have written it in this particular way. Basically, bilinear is a complex number. That's why I have pushed it to the right. I have written it in this way so that we can do a Fier's rearrangement here. Okay, so this will also answer Advait's question earlier. Like, for example, what is the advantage of like having one thing in the bilinear or the other thing? Okay, so we will see that if we just look at this expression, it is not obvious that this is 0. Okay, because if you take lambda bar B, gamma nu lambda C, and you do a Marana flip, then this is minus lambda bar C, gamma nu lambda. Okay, so this is antisymmetric because T1 is minus 1. Okay, so this is antisymmetric in B and C, and structure constant is also antisymmetric in B and C, so there is no conflict. Okay, but if you do a Fier's rearrangement, you will see a lot of features which was not evident. So let us bring this lambda A and lambda B to one bilinear. Then we will have minus lambda bar B, lambda A by 4, minus 1 over 4, lambda bar B, gamma mu, lambda A, gamma mu, and so on. Okay, so I will only do a few terms, and the other terms are explained in my notes. Okay, plus so on. Okay, now consider these bilinears, right? For example, consider the first bilinear, lambda bar B, lambda A. Okay, this has, when you do a Maharana flip, this is equal to lambda bar A, lambda B, because T0 is 1 in 4 dimensions. So since this is an identity matrix, you get T0 when you do the Maharana flip. Okay, and that is 1. So this is symmetric in A and B, but because we have a compact group, this is antisymmetric in all its indices. So this goes to 0. Okay. So similarly, you can prove that lambda bar B, gamma 5 lambda A, right? I mean, this also we can do. So this is also lambda bar A, gamma 5 lambda B. This is also symmetric in A and B index, because gamma 5 will correspond to highest rank gamma matrix, which is 4th rank, so T4. But T4 is nothing but T0, which are both 1. So this is also symmetric in A and B, whereas this is completely antisymmetric. So this will also go to 0. Okay. The term with gamma phi, gamma mu is also symmetric, which you can check. Okay. And the term with gamma mu nu will go to 0 because gamma nu, gamma rho sigma, gamma nu is 0. This property you can check an exercise. The only thing left is this term. Okay. And what you will find finally is that if you call this whole quantity as some big X, okay, all of this together implies X is equal to X by 2, which implies X is 0. Okay. Therefore, del mu J mu is 0. So what all did we need to show that the current is conserved? Okay, we needed the equation of motion for lambda A. We needed the Bianchi identity for the gauge field, so we used gauge symmetry, and we used Maharana flip and Fier's identity. Okay, so all of this together tells us that there is a conserved spinor current, and therefore n is equal to 1 super Yang-Mills has supersymmetry, 1 supersymmetry. Okay, and Friedman and Van Proen, like very uncharacteristically in the book, when they do this, they say that this is so beautiful, like so many things have played into this derivation. If someone doesn't like it, they can go home and watch TV. Okay, but I don't share that view. Like, I think you should be interested in it because this may be useful for physics. So, but yeah, it's okay if you don't find it beautiful but messy. Are there any questions? Okay. So now, does someone have a question?
No, I I unmuted myself to say thank you because you wrote J mu, del mu, J mu and equal to and nothing, and then the long discussion. I was starting to feel pain that it's when now it looks complete. Del mu, J mu equal to 0.
Yeah, okay. Sure. Okay. Yeah. So okay. So now we will discuss something that is different in this. I mean, different in our approach to supersymmetry than what we have done so far, which is that we will do something called as off-shell supersymmetry. And the difference is follows. So firstly, we will see what does it mean to say off-shell degrees of freedom.
So, Subbu, when you said there is conserved charge, so that means we have supersymmetries.
By HLS theorem, yeah, because HLS theorem says that if there is a Majorana conserved charge, one Majorana conserved spinor charge, it must be supersymmetric. Is that okay?
Okay.
Yeah. So I mean, I know this is not the most illuminating way of like teaching SUSI, but then it will become a whole course. So therefore, I avoided from going into more details on supersymmetry because we'll quickly switch to gravity. Okay, by next lecture. So we need to understand like what is off-shell degrees of freedom. Okay, so everyone here I think have seen it once at least, that if you have a gauge field which is A tilde mu in the Fourier in the momentum basis, okay, then the gauge transformation is given by A mu going to A tilde mu going to A tilde prime mu, which is A tilde mu plus I k mu epsilon tilde of k. Okay, this is the gauge transformation. Okay, so now before the gauge transformation, before we knew this, right? So A tilde mu has 4 degrees of freedom, right? Right, because it has 4 components, right? But there is one gauge transformation parameter, okay, and we know that this is not physical, right? Because I mean, if you just substitute any function epsilon tilde here, it satisfies the equations of motion. So these are unphysical degrees of freedom. So to remove them, we do a gauge fixing, okay, which can be done by demanding A tilde mu is equal to 0, okay. So whatever I am calling A tilde mu, like people also call it epsilon tilde mu polarization, but that's basically what I mean. So this is K mu, A tilde mu is equal to 0. So this is the Lorentz gauge condition. Now, since this is one condition, okay, it reduces 1 degree of freedom. So we will have 3 degrees of freedom. Okay, once this condition is imposed, we have 3 remaining degrees of freedom. Okay, for A mu. Okay, after gauge fix. But notice that this does not completely fix the gauge, right? Because if I take, let's say, A tilde prime mu going to A tilde double prime mu, okay, plus some I k mu epsilon tilde k, okay, then this is given by, then we will have k A tilde prime mu, which satisfies the Lorentz gauge condition, okay, is equal to k mu A tilde double prime mu of k plus I k square epsilon tilde. Okay. So now, if you are considering, if you know the equation of motion for the photon, right, that tells us that k square is 0, right? So if you are considering on-shell degrees of freedom, then this is 0. That implies that k mu A tilde prime mu, A tilde double prime mu is also 0. Okay. So there is a residual gauge freedom, okay, which you can fix by demanding A tilde 0 demand A tilde 0 to be 0. Okay, that implies 2 degrees of freedom, and these are the 2 polarizations. So these are the 2 on-shell degrees of freedom of the photon, okay, which is also manifest by the fact that massless gauge field will have 2 helicities. Okay, so that those are these 2 degrees of freedom. But if we did not use this on-shell condition, right, then photon has 3 degrees of freedom. Okay, and these 3 degrees of freedom are called as off-shell degrees of freedom. Okay. Is this clear so far? Okay. So what we will be interested in is, can we have representations of supersymmetry where the off-shell degrees of freedom in between bosons and fermions match? Okay, so let us discuss that a bit further. Okay, so in whatever multiplets we considered so far, for example, let us consider the vector multiplet in n is equal to 1. We had a massless gauge field and a okay, let me call it psi, and a massless fermion. Okay, both of them have 2 on-shell degrees of freedom. Okay. Because ultimately they are both massless particles and they have 2 helicities. Okay, whereas if you count off-shell degrees of freedom, mu has 3 off-shell degrees of freedom, whereas psi is a spinner with 4 real components, right? It's a Majorana spinner. So we have 4 degrees of freedom. Okay? So off-shell degrees of freedom do not match. Okay? Whenever this happens, okay, then supersymmetry algebra closes on the fields up to equation of motion. Okay, so suppose you do one supersymmetry transformation and do another supersymmetry transformation on some field, let's say psi. Okay, then that will go into p slash minus p slash by 2, whatever. Okay, acting on psi, and plus equations of motion. Okay, so when equations of motion are satisfied, supersymmetry algebra are satisfied. So this is called on-shell supersymmetry. And all the field representations that we obtained from our analysis, right, earlier of massless representations, okay, were for these on-shell representations. Okay, because we considered states in the Hilbert space, okay, which are and we used on-shell states. So these are so what we got was on-shell degrees of freedom, so that we can infer how many on-shell degrees of freedom are there directly from representation theory. So let me just formally define off-shell degrees of freedom and then take any questions if they're there. Off-shell degrees of freedom is number of components of a field minus number of gauge transformation parameters. Okay. So we are just refraining from subtracting the residual gauge transformation parameter. So if you have graviton, it has 10 components and it has 4 diffeomorphisms, so it has 6 off-shell degrees of freedom. If you write the Weyl-Bein, then Weyl-Bein has 16 components, E mu A, right? And then there are 6 local Lorentz transformations, which we will see later also, and 4 diffeomorphisms. So you subtract 10. Weyl-Bein also has 6 off-shell degrees of freedom. Okay, is this clear?
Subbu?
Yeah.
So will you be also talking about the cases where gauge transformations also has gauge invariances later?
Sorry?
So for example, if you have form fields,
okay,
they have some gauge transformation of one lower rank form, then those gauge transformation parameters also have gauge transformations and so on.
Yeah.
So will you be covering that case later also?
Yeah. I mean, we will see the tensor multiplet in n is equal to 2 supergravity. So then we will consider this, but it's not relevant for this discussion at least. But yeah, we will do that.
No, I was just asking because in off-shell degrees of freedom, I guess for those fields, you need to be careful about that fact as well, that gauge transformation parameters might themselves also have gauge transformation.
Yeah. So basically what you are saying is, suppose I have a higher rank, higher form, right? Let me call it omega as the field, okay? And then omega goes to omega plus, let's say, d alpha, okay? And this alpha, so if omega is a p form, then alpha is a p minus 1 form. But now I can also take alpha to alpha plus d beta, where beta is a p minus 2 form.
Right.
So we need to be careful about this.
Yeah.
But yeah, okay. Yeah.
So I have a question.
Yeah.
So this thing that you have described, this off-shell degree of freedom.
Yeah.
So does that mean that in your theory, so be it a gravitational theory or a gauge theory,
yeah.
So you don't need to fix the residual gauge freedom if you want to show the like supersymmetry algebra. So even if you don't fix it, ultimately you can get the supersymmetry algebra. It just be there will be an additional term which will be proportional to equation of motion. Is that what you're trying to say here?
Okay, so what I am trying to say is that if you only have on-shell degrees of freedom matching, okay, then you will have these additional equations of motion term, okay. What I have, and it is not generally true that, I mean, what happens is in these cases where it is only true up to equations of motion, the off-shell degrees of freedom are not equal. But you can make off-shell degrees of freedom to be equal by some means, like by adding some other field, which I will explain in the next slide, okay. Then this additional term won't be there. Supersymmetry algebra will be satisfied without demanding equations of motion. Okay? So that is the difference. If you have like supersymmetry transformations for multiplet where on-shell degrees of freedom match, then you will have supersymmetry closing up to equations of motion. But if you have off-shell degrees of freedom matching, then you will have the multiplet obeying the Susy algebra identically. Okay. So maybe it will become clear in the next slide. Okay. So basically what I want to say is on-shell degrees of freedom match implies Susy algebra closes up to equations of motion. Okay. Whereas off-shell degrees of freedom match implies there is some lag. Susy algebra closes identically on fields. Okay, but how do we make it match? Okay. Because as we saw earlier, we had these fields A mu A and psi A, right? So this was in the adjoint representation. For simplicity, let's just consider the vector multiplet, which is abelian. Okay, we had A mu and psi. Okay, A mu has 3 off-shell degrees of freedom. Okay, and psi has 4 off-shell degrees of freedom. So bosonic degrees of freedom are less than fermionic degrees of freedom. So the way you remedy it is by adding a scalar, okay, which has 1 degree of freedom. Okay. So therefore, you will have 4 plus 4 off-shell degrees of freedom. Okay. So if you find a way to add this auxiliary field, okay, into this picture, okay, then you have an off-shell multiplet. Okay, A mu, psi, and D transform among each other, okay, so that the full action is supersymmetric invariant, and the Susy algebra is satisfied on the fields without demanding equations of motion. The advantage of this is that on-shell multiplets are tied to specific equations of motion. Okay, like if I give you some transformation rule, they will only be applicable to that Lagrangian, okay, for those fields. Whereas off-shell multiplets, okay, when you have off-shell degrees of freedom match, when you, for example, have these 3 fields, okay, you can use it to write any action, okay, and the Susy algebra on the fields is independent of that. Okay, so the transformations don't depend on which action you are considering. So therefore, every time you construct a new action, you don't have to change the transformation rules. And this is extremely tedious, especially in supergravity. If you have to both change the transformation rules and equations of motion, it will become extremely tedious. Whereas if you have an off-shell multiplet, where off-shell degrees of freedom match, then it is much simpler. Okay, the only non-trivial part is that on-shell multiplets we could just derive by using on-shell representation theory. Okay, by using massless representations, we can just see what is the on-shell content, whereas there is no obvious way to derive new off-shell representations. Okay, it is highly non-trivial. But if you are able to come up with it, okay, for simple multiplets, you can do it by guesswork. For example, here we needed 1 degree of freedom, so we can say, therefore we need a scalar. Okay, but it becomes more and more complicated for complicated multiplets, like especially higher n supergravity multiplets. But these techniques are extremely useful because they can be used to construct any actions. Okay, and in our course we will see how to do off-shell supergravity.
Subbu, how do your action itself knows about this phi now? So initially you have an action which doesn't include the phi, right?
This is D, but yeah, okay.
Oh, D, sorry. I mean, okay, this scalar field.
Yeah.
So initially you have an action which does not have scalar field, and now on shell with like equation of motion that you derive from the action, using that thing, you have a closure, right? An on shell closure, I mean.
Yeah, in the action, this D will be like an auxiliary field. It won't have like dynamical equations.
Okay.
Yeah.
So when you have, let's say you have given me a off-shell multiplet.
Yeah.
I have a mu psi and D, all of them.
Yeah.
And now, as you are saying, I can now construct any. It will not depend on which action I'm considering, right?
The transformation rules are independent of which action you are
right. So whatever action, so it will now the how this D field appear in the action, that will depend on the equation of motions. Is it true?
Yeah. Usually what happens is that in quadratic Lagrangians, okay, this D will remain auxiliary. Okay. Whereas if you go to higher derivative actions, this D will also become dynamical, but then you have to do a derivative expansion for these fields, which we will probably discuss sometime later.
Okay.
Yeah. But what I mean is that the transformation rule remains the same, and that is extremely useful because every time if you have to change the transformation rule, it will become extremely tedious. Because how do you construct an action? When you construct an action, you should know that the action is supersymmetry invariant. To know that, you need to know the supersymmetry transformation rule. But if the transformation rules themselves depend on the equations of motion, then you have to do a very tedious iterative process. And to avoid it, we add an off-shell field. Yeah, Arna.
Hi. Do you also have to worry about the matching of on-shell degree of freedom?
Yeah. So as I was saying, because of this, in the quadratic Lagrangian, this appears as an auxiliary field. It won't have any kinetic term, and therefore this won't have any on-shell degree of freedom.
Okay. I mean, how many on-shell degree of freedom does psi have?
Both have 2 because they are both massless fields, right? So they both have 2 on-shell degrees of freedom.
Okay, so on-shell degree of freedom matches even without the introduction of the auxiliary field.
Yeah, because that is how we derived it, right? Like we derived using this representation theory. Okay. Their on-shell degrees of freedom is guaranteed to match because we derived it. Remember, like we said, the combinations for odd m and even m, they match the sum of the states, right? Because when we acted these Q daggers, one level was boson, another was fermion, and so on. Okay, and odd level sum and even level sum matched. So on-shell degrees of freedom match for any representation that can be proved. Okay, but off-shell degrees of freedom match would be a nice thing to have because of this reason. Okay. Are there any more questions?
I have a question.
Yeah.
So regarding the fact that you want to try and find the auxiliary field, you're saying that there is no procedure and you have to kind of sort of guess.
Yeah.
So what are the constraints on this auxiliary field? So for instance, if I see, for instance, that option, the bosonic and the fermionic degrees of freedom are differing by say 2.
Yeah.
Why can't I just add 2 scalar fields and be done with it?
Yeah, so you can add 2 scalar fields. The thing is that you will have you will have to write a transformation rule which satisfies the algebra. And in supersymmetry, algebra is algebra is extremely powerful. Like algebra will tell you something is not possible. Because suppose you have this D, right? Consistent with Lorentz symmetry and the fact that psi is a Grassmann number, there can only be a few terms that you can write, which are where the left hand side and right hand side have the same structure. Okay, so suppose you write that, okay, and then you see if the algebra is satisfied. If you choose the wrong auxiliary fields, it will show you the algebra is not satisfied.
Is there something that tells me that there is only one auxiliary extent of this? I mean, given a on-shell multiplet,
yeah,
is there a unique off-shell multiplet that completes it?
No, that is not true actually. I mean, given an on-shell multiplet, there can be multiple off-shell multiplets.
Oh, okay. Thank you.
Yeah. And later on, we will see more techniques. And that discussion will become a bit technical, so I'm avoiding that. We will see how, for example, conformal supergravity provides a more easily manageable way to derive these multiplets. And there possibly we can discuss. Like there are some techniques to derive off-shell multiplets. Yeah, Argo.
So probably related to this one. So let's say there is a mismatch in off-shell degrees of freedom. Let's say for some field.
Yeah.
And now, as Arindam was asking, like you can either look at it as bosonic degrees of freedom, like you included let's say scalars and all, or you could have included fermions as well, right?
Yeah. And then made it bigger. Yeah, that is.
Yeah. So can you just the way you construct these off-shell multiplets? Does it also tells you like what kind of specific field that you have to add?
Yeah, actually, like in the component formulation, right? This is what you have: is supersymmetry algebra, okay, and that off-shell degrees of freedom don't match. What you do is you try to add the minimum number of components, and then you see if that can satisfy the algebra. Okay. What happens is that for matter multiplets, these techniques are simple enough, and this can be done, okay, efficiently. For gravity multiplet, it is difficult, but there are conformal supergravity techniques. We will see how to do gravity as a gauge theory, and that will give us an off-shell representation of supergravity, which we will then take it to construct general actions. Okay? This is how this problem is avoided in conformal supergravity.
Okay.
Okay. Are there any more questions? Okay. So for super Yang-Mills, this will just take an adjoint index A. Okay. A mu A, psi A, D. Okay. You can also study n is equal to 4 super Yang-Mills this way and so on, which we will see briefly tomorrow. Okay. The field content. And okay. So this finishes my basic discussion of supersymmetry and on-shell and off-shell representations. Now we will study the last tool that we need in these lectures before we go to techniques directly relevant to conformal supergravity. Okay. So in the 15 minutes that we have, okay, we will study an extended superconformal algebra. Okay. This is just the conformal extension of the Poincare algebra. Okay. And in fact, I have been a bit careless whenever I said Coleman-Mandula theorem, HLS theorem, and so on. I should have mentioned that if there are massless fields, these theorems also allow the conformal extension of that algebra. Okay. So, of course, Coleman-Mandula theorem does not forbid the conformal algebra, for example, in space-time for massless fields. Okay. So, similarly, massless fields can have an extended superconformal algebra. Okay. And so this algebra people often write as SU2,2/n, okay, which looks a bit scary. But basically what this means is that, SU2,2 is locally isomorphic to SO4, 2. Okay. And this, I think people know in this audience that this is the conformal group in 4 space-time dimensions. Okay. So there is some lag, but I hope it will appear. So this we know is the conformal group in 4 dimensions. Okay. So now, if we and this n,
can you elaborate on the part locally isomorphic?
Oh, what I mean is just like SU2 is, the algebra is isomorphic to SO3.
Yeah.
So here also there will be some simply connectedness feature which will affect the global result. Okay. But that won't be relevant for us. The algebra is the same. That is what I mean by locally isomorphic. Algebra has the local information, and that is the same. Okay. So these are the only 2 SU and SO algebra isomorphisms or root homomorphisms that exist. Okay. So that is this. So this is just conformal group in 4 dimensions, okay, which is derived in any book which has conformal symmetry studied. Okay. And these n are the number of supercharges. Okay. But now, we already have the conformal algebra which has these generators, translation generators, Lorentz transformation generators, dilatation generator D, and Ka, which is the special conformal transformation generator. Okay. So now this we are clubbing with the supersymmetry generator Qi. Okay. But then what you will notice is that when you take the commutator of K with Qi, okay, if it has to go to anything, okay, then that must have a gamma A because that is the natural object with a flat index. And then we will call this Si because this has to be a fermion. Okay. And this is called as special supersymmetry, okay, which is specific to superconformal algebra. Okay. In superconformal algebra, whenever someone says there is n is equal to 1 supersymmetry, they mean that there is 1 Q and 1 S. Okay. So this is special SUSY, and in superconformal algebra by Jacobi.
Okay, just one question that with the SUSY supercharges Qi, we know that it mixes the bosons and fermions. Then why do you? Then are you assuming that the conformal algebra that you have is defined on bosons? Because then otherwise, why are you saying that the Si on the right hand side is a fermionic? I labels the fermionic index.
Yeah. So this conformal algebra is the usual conformal algebra of the bosons. And we are trying to construct a full superconformal algebra. So instead of just giving the algebra, I'm just telling you, if you begin with conformal algebra and supersymmetry separately, how will you get the superconformal algebra?
Okay.
And
okay,
because
so
this is not a Grassmann number, this is a Grassmann number.
Okay, yeah. Mm-hmm.
Okay. Yeah. So this is special supersymmetry. And now you might think these are the only generators, but because okay, and Si is another one. But what you will see if you use Jacobi identities, that this algebra necessarily has an SUN cross U1 R symmetry. Okay. So this R symmetry, I could have even done it in flat space. I could have even done it in Poincare-SUSY discussions earlier. Okay. It is basically you have some generator T, okay, which when it acts on Q, okay, it's proportional to Q. Okay. So it can exist for only some supersymmetric theories. In Poincare supersymmetry, this is not necessitated by the algebra. Okay. Like even without this T, SUSY algebra is closed. Okay. Whereas there is no superconformal algebra without these. Okay. There is some technicality in n is equal to 4. There is no U1, it is just SU4. But other than that, Jacobi identities, if you analyze it for each n, okay, they always have this R symmetry. Okay, so this is a part of the algebra itself for superconformal algebra. Is that point clear?
I have a doubt.
Yeah.
What is this R symmetry like SUNR, and also these two new generators that you have written, lambda I new.
Yeah.
So is that a semicolon or S dot? What is that dotted indices? Like.
Oh, this is lambda Vij. Okay. So this is the SUN index, and this is in the adjoint representation. Okay, because these are generators. Okay.
Okay.
So this would be this is like traceless anti-Hermitian property. Okay, and this is the U1 generator. Okay, and I will write the action, and then I will take the next question. So del V Qi is lambda Vij Qj. Okay, and del V Qi is minus lambda Ji. Okay, and if you look at S, then it is the same with Q replaced by S. Yeah, Arnav. Yeah.
So this T is the generator of what? Lambda T or the full SUNR cross U1 group?
Yeah, you could just write lambda T. Yeah, I just meant like in SUSY, okay, people write T usually, but yeah, like, yeah.
Sorry, I couldn't understand. T.
Okay, maybe I'll just use T once.
Okay, it's for the U1 generator.
Yeah.
And also, like,
I mean,
can you tell me the count of the number of generators? So this conformal algebra that you have written down has 15 generators, right?
Yeah, 15 generators.
And then the rest, Qi, Si, and those generators, that will be like total how many generators will be there?
Oh. Okay, we'll count it later actually. In the next lecture, when we construct like conformal supergravity multiplet using gauge theory of this algebra, okay. We will count it. Okay.
No,
I mean, I can count it now, but I'll.
No, that's all right. I mean, I just wanted to ask, so is it required that the number of fermionic generators and the bosonic generators will be the same?
No, that is not required. Okay. Yeah. So this will be relevant tomorrow. I will mention it. Okay. Okay. So this is the.
So what does SI do? Like QI, and I understand it takes fermionic states to bosonic states and the conformal. So what does SI do exactly?
Yeah, SI also takes bosons to fermions, right? Because SI is like.
So it's also a fermionic.
Yeah, but what we will do is, like even though okay, how do I say it? Like there are people who study like superconformal field theories, okay, who will study representations of this superconformal algebra, right?
Okay.
But for us, like in these lectures, these are a tool to get the Poincare algebra. I mean Poincare supergravity in the end. Okay.
Okay.
So we won't study the representation of the superconformal algebras. So I won't be able to tell you like what S creates or annihilates, and I would defer it to like Slack or something, so that like people who are experts in SCFT can answer them.
Okay.
Hi, Subbu. Hello.
Yeah, hi.
Probably you said that about this. So I just wanted to know that why do you need this R symmetry?
Yeah, so otherwise this algebra won't satisfy Jacobi identities.
Okay.
So there are certain commutators, like once you add S, okay, you will have certain Jacobi identities which won't give you 0. Okay, but if you add generators like this, they will give you 0.
Okay, nice.
So I should mention all of this was done by Nahm in 1972. Okay, the classification of super algebras, okay, which satisfy the whatever are our requirements from the theory.
Subbu? So like how the special conformal transformation generator and the Qs, they have that algebra. Is there a similar algebra for P's and S?
Yeah, P's, P and S also goes to Q. Yeah.
In exactly the same way.
Yeah, exactly the same way. Yeah.
I see. Okay.
Yeah. So this, you can derive it also from the Jacobi identities. Because suppose you act another P here, right? PB, right? Then you know, like P commutator with K, you know, K with Q, you know. The only thing left is like P with Q. Sorry.
Right.
Sorry. If you do it on the right hand side also, right? Then that will give you P with S. Okay. And P with Q, you know, it is 0. P with K, you know. K with Q, you know. So P with S is
right.
Hi, Subbu.
Yeah, hi.
So I had another question about this R symmetry group. So we start with Poincaré and supersymmetry algebra, right? Both are space-time symmetry.
Yeah.
So so now to close the so we are trying to extend these two symmetry group to superconformal algebra, and the R symmetry is kind of there to close the two symmetry group. I mean, right? So,
if you consider HLS theorem, okay, for superconformal algebra, it will come along with these R symmetries.
Okay. Thank you.
Okay. So this is a major difference, that superconformal algebra always has the R symmetry. Okay. So, and it acts in this way. So Q upper J's are in the fundamental representation of SUN, okay, and Q lower J's are in the anti-fundamental representation of SUN. Okay. And this Qi, okay, we knew it's gamma phi eigenvalue, okay, was -1. Okay. This implies that gamma phi Si is plus Si, okay, because there is another gamma A here. When you interchange gamma phi with gamma A, you get another minus sign. So this has this chiral. Okay. And perhaps one more thing that was 2 minutes. Yeah. So one more thing that I should have mentioned earlier, you know, because Majorana condition relates psi star with psi, okay, this implies that the usual UN symmetry does not take place. Okay, like the U1, I'm giving just an example of U1. U1 is chiral. Okay. So let me elaborate it in the next slide. Okay. So because psi is related to psi star, okay, is proportional to some operator times psi star, okay, or the other way around, however you want it. Okay. If you just take psi going to psi prime, which is e to the power I theta psi, okay, it is not compatible with the Majorana condition. Okay, not compatible. Whereas if you have psi prime going to e to the power I gamma phi theta, which will have like the opposite charge for like chiral and anti-chiral spinors, that is compatible with Majorana condition. So for Majorana spinors, symmetries are always realized as chiral symmetries. And therefore, in the earlier slide, when I said there are SUNR and U1R symmetries, these are realized as chiral symmetries. So for one chirality, it acts as the fundamental representation, another is an anti-fundamental representation. If one chirality has one charge under U1 symmetry, the other chirality has the opposite charge under U1 symmetry, and so on, which we will see in the next lecture. Okay, so I am done for today. So tomorrow we will complete the discussion on the superconformal algebra. So in the recap, I will go through these things again, and then we will see in an example without supersymmetry how to construct a gauge theory of the conformal algebra and gauge fix it to obtain a theory of Poincare gravity. Okay, and so from conformal gravity we will get Poincare gravity by gauge fixing, and that is what motivates us to do the same thing with supersymmetry, because Poincare supergravity theories are extremely hard to construct, whereas this method is extremely convenient. Okay, so I am done. If there are questions, I can take.
Okay, let us thank Subbu for his lectures. So since we are a bit sort of late on time, maybe we will pause the recording now and people can ask questions more informally to Subbu. And we start the last lecture precisely at 4:30. Okay, welcome back. So let us start with the last lecture of today. Biswajit is going to continue talking about soft theorems. Over to you.
Okay. So I'll just start by recapping what we discussed in the morning. So in the morning, we derived single soft photon and soft graviton theorem up to subleading order in the soft momentum expansion, basically analyzing these two sets of diagrams. And we have seen how to compute this thing from the covariantized action prescription. And let me show what is the result what we have gotten. So this is the result I have written again for the single soft photon theorem. So you can see this gamma n plus 1 is basically the n plus 1, like the n number of finite energy particles, and one of the particle which is photon or graviton, and it is soft. It has momentum k and polarization epsilon. And this we have expanded up to like a subleading order in the k expansion. And we have able to relate this thing in terms of the amplitude, which is which does not contain this soft photon or graviton, which we promised in the beginning of this lecture series. And what we have shown is that, like, so the leading soft, like we have got in the first line, the leading soft photon and soft graviton theorem is written. So let me make again this color code thing. So let me like put a tick and cross. So this is the leading soft photon theorem. And in the subleading order, we have seen that this is the subleading soft photon theorem with also this term, which is the non-universal piece, theory-dependent piece appears in the subleading order of soft photon theorem. Then in the soft graviton theorem case, we have seen that up to subleading order, it is universal. And the cross terms are basically represents the subleading soft graviton theorem. One can identify this just looking at this polarization epsilon mu nu. This is the graviton polarization. On the other hand, epsilon mu is the photon polarization. So if you just look at this thing, you can see that like the leading order, what is the difference between the leading soft factor for the photon and the graviton? You can think of if there is one less polarization index, and if you replace the charge of the particle by another momentum, then basically like these two things will be replaced. Like if you have a epsilon mu pi mu, and suppose the charge of the particle is qi, so we basically replace qi by another p and increase one of the index mass, make it epsilon mu nu and pi mu and pi nu. Then you see that you will get the leading soft graviton theorem. In that way, you can do also at the for the universal piece of the starting from the universal piece of the subleading soft photon theorem, you can also go to the subleading soft graviton theorem piece. Here I just want to note few points. So later I will use some compact notations for that. You can see here in the box, I have combined in the subleading soft graviton factor some term appears, which you can identify with the total angular momentum of the ith particle, where basically these first two terms are basically the orbital angular momentum, and then this is the spin angular momentum of the ith particle. So later I will denote this total sum as total angular momentum by JIAB. And you can see, like, if the particles, like if you are considering say only for soft photon theorem, then if the particles are eigenstate of this charge matrix Qi, then you can always use like Qi times epsilon I to be the charge of the particles Qi and epsilon I. Okay. And N basically corresponds to the non-universal term, which contains the non-minimal coupling Ci mu nu, and some other theory dependent part coming from the kinetic term of the particle finite energy particles, and it's also propagator contribution. So this is roughly the structure of the single soft photon and soft graviton theorem up to subleading order. Now we want to see that, like suppose now we want to study the double soft graviton theorem. So let's now for a moment forget about the soft photon piece, only focus on the soft graviton piece. Okay, so for that case, let us, and if we want to study, say, double soft graviton theorem, so up to the subleading order. So what kind of diagram contribution can be there? So first of all, I can explain that, like, if suppose, like, say the first kind of diagram where one of the particles momentum is pi, the other particle's momentum is pj, and say one of the graviton momentum is k1, the other graviton momentum is k2, then you can see the momentum flows in this line is pi plus k1, in this line it is pj plus k2, and from these two propagators, if you just use the on-cell condition for the ith and j particle, that basically gives a contribution like pi dot k1 times pj dot k2. So you see, this is 1 over omega square contribution if you consider k1 and k2 both have the energy of order omega. So this kind of diagrams, which involves only vertices of gamma 3, that is 2 finite energy particles and 1 graviton, that contributes at the leading order, and for the double soft graviton theorem, it turns out to be 1 over omega square order at the leading order. So similar one, another kind of diagram is this diagram, and here also you can see like only gamma 3 vertices appears, and but both the graviton connected to the same line. You can show that this diagram also contributes to the leading order and also contributes to 1 over omega square. Now you can see that there are other diagrams, but the other diagram starts contributing at the subleading order. For example, let's focus on this diagram, say. So here, suppose if this diagram, the momentum is pi, and suppose these two graviton had momentum k1 and k2. So here the momentum flows in this propagator is pi plus k1 plus k2, and you can see that this diagram will give a propagator which goes like pi dot k1 plus k2. So this gives like contribution at order 1 by omega, and you can see that in omega expansion 1 by omega square is the leading, so 1 by omega is the subleading contribution. So this diagram starts contributing to the subleading order. There are other diagrams, this diagram where one of the graviton is connected to gamma 3 vertex, other is directly connected to some internal line. This also you can see due to the presence of one propagator, it also contributes to order omega. The other kind of diagrams possible is basically when suppose two of the gravitons connect to via another graviton, and this another graviton connects to gamma 3 vertex. Here also, since there is only one finite energy propagator, so that will give a 1 over omega contribution, and you can see the other omega contributions coming from this 3 graviton vertex, and the graviton propagator cancels among themselves. So this also contributes at order 1 by omega. So these are the sets of diagram one have to compute if you want to analyze the double soft graviton theorem. So up to this point, is there any question?
Biswajit?
Yes.
So this is for the simultaneous double soft, right? If you have a consecutive double soft,
right?
Like, will all the diagrams contribute, or can you tell like which of the diagrams can be on?
At least I can say that the last diagram will not contribute.
Okay.
In the consecutive limit, but also like some of the contributions coming from the other diagrams also goes.
I see. Okay, thanks.
Okay. So now with this understanding, one can ask the question that, okay, so obviously I can start from m equal to 1, m equal to 2, and m equal to 3 always, but can we really get any general for any general m, like any m number of soft graviton up to subleading order result can we derive just from the understanding of single soft graviton theorem and double soft graviton theorem? So the answer is yes, we can do this thing. Even but it turns out that we don't need no other ingredient, only the vertex, which is we define as gamma 3, which is 2 finite energy particles, 1 graviton, and the vertex which is used as gamma 4 in the double soft graviton theorem involves 2 finite energy particles, 2 graviton, and the another kind of vertex attached by via gamma 3, which is basically 3 graviton, like 3 graviton vertex. Only this kind of vertex would be enough for analyzing the multiple soft graviton theorem. One don't need any more ingredients beyond beyond the ingredients what we need up to double soft graviton theorem to prove the multiple soft graviton theorem. And the reason is that one can think that, okay, why not, like if you are studying multiple soft graviton theorem, there can be say 3 number of gravitons are connecting, in the same vertex. You can see this kind of diagrams could not contribute, because now when 3 of the gravitons connect, like for m number of gravitons, if the 3 of the gravitons connect, then basically you will have now m minus 2 number of finite energy propagators, and that will give you 1 over omega to the power m minus 2. But the leading order contribution for m number of graviton, as we see, will go like 1 over omega to the power m. So the subleading order is omega to the power m minus 1, and omega to the power m minus 2, 1 over omega to the power m minus 2 goes to the subleading order. So this kind of diagrams we don't need to compute. Like this kind of any diagram which contains suppose 3 gravitons connect to the same vertex, we don't have to analyze. Similarly, you can think of that, okay, let me erase this thing. You can think of some other kind of diagrams, say same gamma via same gamma 3. One graviton is connected, and say here is a 4 graviton vertex. Can this contribute? Like if any diagram contains such kind of vertex for analyzing m soft graviton case, can this contribute to subleading order? The answer is no here, because first of all, since again 3 of the gravitons connected, so obviously now one have a m minus 2 number of finite energy particles propagator, which gives a factor of 1 over omega to the power m minus 2. And then this 4 graviton vertex, since it comes from square root gr of the Einstein-Hilbert action, obviously there could be higher order terms, but those will be more, those will contribute at more and more higher order. But for the even from the square root gr, you can see that the 4 graviton vertex also contains 2 derivatives, because it's a 2 derivative theory. So 2 soft momentum it will contain, and the propagator also contain a 1 over like k1 plus k2 plus k3 square. So it is also contains like 1 over omega square order, and these 2 effect cancels. So again, the full any diagram having this kind of vertex and all the other vertex which are only gamma 3 and connecting one single graviton, these also don't contribute, because that start contributing at subleading order. So it turns out that only and up to, if you can understand the derivation of the double soft graviton theorem up to subleading order, it would be enough to get the result of multiple soft graviton theorem. But the proof is very much involved, and for that I will suggest to look the references which I mentioned in the lecture note, which I have already uploaded in the Slack. So let me, yes.
The last diagram, the 4 graviton vertex.
Right.
So for Yang-Mills, the 4 graviton for gluon vertex does not have any momenta. I mean, it's just a coupling.
4 gluon vertex.
Yeah.
Gluon,
Yeah. So
right.
I just want to know what is the like. Are there momenta components in the 4 graviton vertex?
4 graviton vertex always has 2 momentum, right? Square root gr. So you expand r up to a order like 4h term.
Oh
right?
yeah. Yeah.
But anyway, r contains always 2 derivatives.
Right. Okay.
So it has the 2 momentum. So you will not. But that is why in case like I think one of the open problem in my lecture note I mentioned that for QCT case, if you try to derive multiple soft gluon theorem, even like to derive at the leading order, you need m, like if you want to derive m soft gluon theorem up to m number of gluon vertex you need to analyze, and this is infinitely hard problem.
Okay. Okay, thanks.
But isn't it true that this 4 gluon vertex can be replaced by gauge fixing to 3 gluon vertices, right?
Yeah, but that you can do, but still the momentum dependence will not go probably.
Because 3 gluon vertices have a less complicated momentum dependence.
Right. Even I think like, okay, let me then go in little detail. What happens is that even the things will be complicated even if there is 3 gluon vertex only is there. Because you see there could be a diagram where trees of diagram, even via 3 gluon vertex, this kind of diagrams could be there. Okay. And like all these kind of diagrams will contribute to the leading order. If such kind of diagrams are present, you can show. Because the thing is that like for gluon case, the vertices for suppose 3 gluon vertices, those is linear in momenta. On the other hand, for gravity case, this is quadratic in momenta. So the momentum suppression from the vertex, like 3 gluon vertex, will be like less power of momenta than the graviton, and this basically keeps like you have to analyze further and further and further kind of diagrams.
Biswajit?
Yes.
And I think somehow the loop diagrams also become important, right? I mean, in gluon soft theory.
Yeah. So, but we are considering say in higher dimension, probably in higher dimension one can start with your effective action and things will be simple. Yeah. In 4th dimension, obviously, this is much more complicated. We can discuss. Well, we'll discuss the 4th dimension.
Oh no, what I mean is like for the soft gluon, right? For the soft gluon, we write this action, right? This F mu. Right. So that is not like a 1pi action or anything. That's just
right.
Yeah. From that action, I think you will have some loop diagrams.
Yeah. Right. So this is even pre-level. It is very complicated. You see, like loop. Obviously, loop one can show that you will say in like loop there will be much complication will arise.
Okay.
No, but I didn't understand this. In higher dimensions, if you're considering 1pi effective actions, so then basically the analysis reduces to tree level.
Right. In higher dimension, if one have 1pi effective action, it's correct. But Subbu is telling that suppose one give a Lagrangian F mu nu. This is just general Lagrangian, and try to derive loop like diagrams which have loops also, and try to derive soft
because
theorem.
That is already there in the soft covariantization setup, right? For the soft particle, you don't have the 1pi effective action, right? You have the quadratic action for that particle.
Right, but that already involved in the definition of the 1pi vertex, right?
Yeah. So, I see. Okay.
I think I like the 1pi vertex.
So I guess the subtlety is only in 4 dimensions. Okay.
Yeah, in 4 dimension, like a 1pi effective action construction is difficult.
I see. Okay.
Right?
Yeah. I think 1pi effective action construction is not difficult because this is off-cell thing, and off-cell there is no IR divergence issue, right? So 1pi effective action is off-cell statement. There is no problem. Now one of the assumptions is that the vertices cannot contain denominator soft momentum. This is the problem which will break down.
Okay.
Off-cell you can the off-cell 1pi effective action you can always get.
Okay. Just a sort of speculative question: cannot one use double copy to get soft gluon theorem from the soft graviton theorem, at least at the key level in higher dimensions?
Yeah, I think this Manu Atira, they have worked on this thing in the classical limit, at least tried to derive this thing. But I think in their work also they assume that this kind of contact terms which will appear due to this multi-gluon contact terms, those will be suppressed relative to the other soft leading like S0, S1 and other factors. And in that way it works. But yeah, there may be subtlety. They may explain better.
Manu, you have something to say?
Adira might explain. No? Last time I took all the explanations.
Sida, you're there?
Yeah.
No, what Biswajit said is correct actually. So the
what happens? I cannot.
Manu, Atira, both of you are muted. Can you just unmute yourself?
Oh, sorry. Yeah, so I was saying like Biswajit is correct. Like the contact terms are actually suppressed by they go as order 1. So you don't have to consider like for the leading case, at least in d greater than 4, you don't have to consider for the leading gluon soft theorem. The contact terms are proportional to f, like the the structure constants, and from that you can show that the contact terms don't matter, at least for the leading case.
Yeah, but in the classical limit only.
In the classical limit only.
Right. Not in the amplitude.
That is important. Yeah.
Mrityunjay, I think, has a question.
Hi, Mrityunjay. Can you ask?
Mrityunjay, you can unmute yourself and ask.
Maybe I can proceed, and if he asks, you can.
He's unmuted now.
Okay.
Hello.
Yes, we can hear you.
Conceptual question. So in this double copy thing, so suppose you consider the leading soft graviton and soft photon theory.
Soft photon. Okay.
Yeah, and soft gluon.
Okay.
So double copy allows you to construct, other one by knowing the first, one of them, no?
Right.
So if you think from the perspective of symmetries, then we know the leading soft graviton follows from diffeomorphism invariance, and the leading this for gluon it will follow from some U1 symmetry.
Okay, maybe SUN symmetry. Okay.
Yeah, color.
So is there? So does it hint that there is some kind of connection between these two?
Yeah, in the multiple, in the like single soft graviton or soft for gluon theorem, one has the understanding the map clear. But in the multiple one, I think only in the classical level higher dimension it is understood.
From the double copy.
From the double copy, I think Manu and Atira they wrote a paper in the classical limit understanding.
A single one also follows from the symmetry argument. No?
Yeah, single one. I think single one just directly the amplitude prescription, whatever one replacing statement that replace some color trace, like trace of the color generators by the corresponding momenta expressions or the like the three gluon vertex expression corresponding. If you just replace, one can relate.
Okay.
I think one have some understanding for the single one. So let me give the expressions for the multiple soft graviton theorem up to subleading order. So obviously this involves a lot of details to derive, but let me give the expression and let me explain what are the different terms are. So this is, you can see, so this is the n plus n and m. So n number of high-density particles and m number of gravitons are involved. Graviton polarizations are denoted by epsilon r with momentum kr, and the finite-density particles are momentum pi and epsilon I to be the polarizations. And the first line is basically the leading soft graviton factor, where S0r is basically the leading soft factor. Let me write it down. So I equal to 1 to n epsilon r mu nu pi mu pi nu upon pi dot kr. Right. This is what I am denoting by S0r. Similarly, you can see the second line, which is the subleading, which is one part of the subleading soft graviton factor, which you can see involves m minus 1 number of leading soft graviton factor and 1 subleading soft graviton factor. So S1 is the subleading soft graviton factor, which has the expression is like summation over I equal to 1 to n epsilon. So let me put S, so epsilon S mu nu pi mu k rho upon pi dot k times ji rho nu. This ji rho nu is the total angular momentum, which I defined earlier, the orbital plus the spin angular momentum. Okay. So this is one part of the subleading soft graviton, like the multiple subleading soft graviton factor. The other part, which you can see, involves a two particle sum r and u, which is, and this is like a pairs, and this, so this is basically pair of soft gravitons are connecting in a sense. Such kind of diagrams contribute to this, and you can also identify what will be the propagator structure. It is like 1 over pj dot kar plus ku. So this is like, you can think of like two of the gravitons with momentum kr and ku are connecting through the kind of diagrams, and this kind of diagrams gives the contribution. In a sense, you can think of this diagram and this diagram roughly contributes to this contact term, because each of this diagram, this propagator has a momentum like pi dot k1 plus k2 for the double. Now in multiple way, now any kr and ku can connect it to the gamma 4 vertex and through the gamma 3 vertex with the 3 graviton vertex, and contributes to this contact piece. So this contact piece also has a very large expressions, but I have not written down the full piece, but just to give the feeling what it is look like. So I just have written in small font. Maybe I can zoom it. So you can see that it contains like 1 over pj dot kr inverse, 1 over pj dot ku inverse, and then some kr dot ku factor, and then other polarization connected to the momentums. So this is the kind of thing. And the other thing is that there contains a 1 over kr.ku. So this is precisely comes from the involving 3 graviton vertex, because if some kr and ku are connected to a 3 graviton vertex and the other graviton has momentum kr plus ku, and that propagator will give a 1 over kr.ku. And this is the contribution coming from this, and the rest contribution coming from the other diagrams. So this is the contact terms, and the result is fully universal, theory independent. Okay, so this is the general structure of the multiple soft graviton theorem up to subleading order, which naturally you can see basically it looks like leading soft factor to the power m, and then leading soft factor to the power m minus 1 times subleading soft factor, and then some other contact terms. This is the general structure for the multiple soft graviton theorem. So is there any question up to this point? Because I will use this multiple soft graviton theorem later in my lectures. Okay. Now I will start studying that, starting from this multiple soft graviton theorem. So what you can think of this multiple soft graviton theorem is basically like a Bremsstrahlung process, like some scattering is happening, multiple number of graviton is emitting from this process, and some low energy graviton. So this is some low energy Bremsstrahlung process, and I want to take its classical limit. Whether from this soft graviton theorem, whether one can relate it to the gravitational waveform. This is the goal of the rest of my lectures. So,
Subbu, you had a question?
Yeah, so the question is, like, when you do this, are the simultaneous soft theorems enough? Because like there could also be low energy particles emitted through, which are like more soft compared to the other, and so on.
Okay, like if we assume that our theory has, okay, I think this is a more generic theory, so you can think that there could be photons and other things also emitting.
No, what I mean is like photons themselves, right? But you considered like simultaneous soft theorem, right?
Right.
All the soft particles are soft at the same order, right?
Right.
Like, but something could scale as tau1 and some other particles could scale as tau2, which would be like consecutive soft theorem,
right?
But from the perspective of the amplitude compared to hard energy particles, they are all soft.
Right.
Right. So why would that not be needed and only the simultaneous one is needed?
Okay. So like here the question what I am asking is that suppose all the particles have the, like obviously in the scattering process you cannot like say that how many numbers of gravitons will emit, what will be the energy of the particles, all these things. So in scattering process, we are fixing the initial and the final particle states, and we are asking the question that what will be the scattering amplitude.
That is true. Yeah.
So in that sense, I am asking the question here is that if all the m number of soft gravitons have same order of the energy, then what will be the, how the amplitude will factorize? You can ask that some of the particles have this amount of energy, some of the particles other amount of energy, how the factorization will hold. But this will be the more general result, and from there, using this kind of scaling, you can extract the result what you want.
Yeah, actually, my question was like with the classical result, like about this process. But okay, I guess that by the fact that they will have the soft particles will have different energies, probably they won't construct the same coherent state. Maybe.
Yes, right. So we will ask that at some particular energy level, what will be the classical limit?
Okay. That's why the simultaneous one is enough.
This will be the simultaneous, but I will show that in the classical limit, actually it turns out to be the consecutive limit. Like I will explain.
Okay.
But I think my screen is frozen.
No,
it is working.
We can see it, right?
Okay. It's changing? Okay.
Yeah, everything's fine.
So we will study the classical limit of soft theorem. So let me start by the simple understanding of soft photon theorem. Then if we understood there, I think soft graviton theorem generation would not be that much difficult. So the question which you want to ask for the soft photon theorem, we know that like if some classically what is our understanding is that if some macroscopic charged object, like it has some charge which is much greater than the charge of an electron, some large charge object, and suppose some such kind of objects are scattering, and they will emit some Bremsstrahlung of photon. And classically, we will expect that at large distance, if we put a detector, I can detect some electromagnetic wave or electromagnetic radiation. So the classical limit corresponds to, it seems that like obviously one single electron or like two electron scattering, there only few number of photons could be present, and that one cannot detect as a like classical electromagnetic wave. This is completely a quantum process. But for the classical limit, one needs a large number of photons should come out, and that like needs that the objects which are involved in the scattering have large amount of charge in the unit of fine structure constant. So the expectation, classical expectation, is that some macroscopic charged object scattered, scattering is happening, and that emits some electromagnetic wave. Okay. So then how, like in quantum S matrix, how we can imply this argument that how we can take the classical limit from a S matrix perspective? So that we can do if we just start with multiple soft photon theorem. Multiple soft photon theorem, which is basically charges of the particle qis. Those are much greater than square root over alpha, where alpha is square upon 4 pi. I am putting h equals to be 1. Okay. So in that limit, if we can show that the number of photons which are emitting is very large, even for fixed omega, then we can say that okay, we can have a large number of photons coming out with energy omega, and some we fix the polarization, say some particular polarization, and we can declare this large coherent state of photons to be electromagnetic wave. So the process what we are considering is, suppose some charged particles are scattering is happening. So let me, some charged particles are coming in, they are going out, they are doing some radiation, and I am at distance r from roughly the scattering center along in-hat direction. This is my detector position. And I want to ask the question, okay, along this direction in a solid angle, so the solid angle is delta omega, and I am allowing a small variation of energy, say from energy omega to omega times 1 plus delta. So this delta omega you can think of in small limit, basically the differential d omega. So within this energy range omega to omega plus delta omega, I want to get that what will be the probability of m number of soft photon emission. Okay, this is the question which you want to ask. So for that, let me at least at the leading order, let me write down what will be the multiple structure of multiple soft photon theorem. For simplicity, I'm just considering the leading order. So this will be the electromagnetic soft factor for earth polarization and with momentum kr, and then gamma n comma 0. And I want to ask that with particular polarization epsilon within energy range omega to omega plus omega delta and within solid angle delta omega, what is the probability number of soft photon emission. So this is the question precisely which we want to ask. And the answer for this turns out to be basically you have an amplitude. So like I have given a form of the amplitude. So you basically do a mod square of this amplitude that will give a probability of a number of particles, but also since I fix some energy value and some direction and also some solid angle, so I have to multiply for each of the photon by their phase space factor, and also I have to divide by a symmetry factor because now all the photons are basically identical. So this probability which we want to ask is basically S0 is the leading Soft factor, electromagnetic with say polarization epsilon and momenta k mod square. Then there are m number of, so 2 to the power m, because there was like m number of such kind of leading Soft factor is there, and we are making it mod square. Then for each of the particles I have to multiply by the phase space factor, which is omega to the power d minus 2 omega delta 2 pi whole to the power d minus 1 upon 2 omega, right? I think this is the phase space factor. And then for each of these photon there will be this Soft factor, so that will be power to the power m. But this is not enough because actually all of the photons are identical, so I have a symmetry factor 1 over m factorial. So this is the probability question what we are asking, or maybe I think this is the differential cross section in a sense you can think of. Okay, so let me write in a compact notation this to be a to the power m upon m factorial, where a is times, okay, I have not multiplied by the solid angle, sorry. So there is a solid angle multiplication also, delta omega upon 2 pi to the power d minus 1 into 2 omega, right? Now what I so is that, like, you see that this epsilon, like if I want to take the charge of the particles to be large, and if you see the expression for this S0, this is like Qi epsilon mu Pi mu upon Pi dot K. So for a particular momenta K, this basically PP order cancels, and if the charge Q goes like lambda, say, then this goes like lambda for Q going to lambda, and we are taking this Q in unit of square root alpha. So this S0 is basically large. So A is a large number, and we demand that there will be large number of photons should come out. So I can extremize this d sigma differential cross section with respect to m to find that how many number of soft photons are really coming out, because in a classical process it's not a probability that particular energy there are many number of soft gravitons are coming out, but it's a particular number I should expect, and I will extremize this d sigma and see that whether all my assumptions are going right. So this d sigma expression which I have is like a to the power m upon m factorial, and a is a large number due to charge of the particle Qi is much greater than natural unit electrodynamics. And I want to extremize this with respect to m. So I take for simplicity, I take a log. I want this thing to be 0, and I want maximum number of gravitons should come out if you take the functions at like, so if you do this thing, it turns out that m is in order of a. And if you take the second derivative, you can find that at m is order of a is always less than 0. So this is a maximum. And you can draw a profile. And you can see for large value of like it basically has a peak at the value when m is equal to a. And you can also compute what will be the standard deviation. So it turns out the standard deviation to be a, the square root a. So you can see for large a, square root a is much less than a, so it will be sharply peaked. And the large number, like since a is large and the peak is happening at m equal to a, so m is the number of soft photons are coming out. So really a large number of soft photons are coming out. So you find roughly in classical limit how many number of soft photons are coming out from the scattering process. Now having this, you can compute that, okay, what would be the energy of this soft electromagnetic wave. So the energy of this electromagnetic wave with some particular, all the photons are with in omega to be their energy. So to be m number of photons are coming out, each of them are energy of omega. So m omega would be the energy, and that is nothing but a omega. And if you just substitute the expression for a, what I have written.
Sorry, Biswajit, one question.
Yes.
That the probability distribution that is showed here, shouldn't it be sharply peaked? That means
it is sharply peaked. Yeah, so I can get the variance is square root a, and like if so, if you just compute the variance, it turns out to be square root a.
Okay, I mean,
okay, and you can see
that
like
be expected to be inverse of something, inverse of square root of a or something, because a is large number.
Yeah. So but if you just compute, it turns out to be square root a. And now what happens is that so with respect to the peak, if you just see the like where you can see that the variance basically turns out to be like near the peak, means it's very sharp, means the distribution though I have drawn, like if it is a very sharply peaked, you can see that the half, when it reach half of the probability, it is very near the very peak. So in that sense, like it is sharply peaked. But you can a large number, say a 10 to the power 30, so you can see square root is like 10 to the power whatever, I don't know, but that will be much less than like 10 to the power 30. In that sense, it is sharply peaked. Yeah, maybe the expectation is that 1 over a could be there, but like just computation, this is what it turns out, and it is still very small compared to m equal to a. Okay, let me just see where I have written the expression for a. So a is here. So let me copy paste it. Into omega. So this turns out to be the energy, like if some photon is in m number of photon is coming out with each of them have the energy omega. But now this is what you have gotten just from taking the classical limit of the multiple soft photon theorem. You can have an independent understanding from the classical analysis. Like this is considered this is a classical scattering, and you just solve the Maxwell's equation and try to find what will be the gauge field, and then from there try to compute that, okay, what will be the energy momentum tensor, and from there you can compute also the energy flux in some delta omega solid angle and some from omega to delta omega. You can independently compute and you can compare these two things, right? So that is what I will describe now. And then relating these two things, what I will do is that I will relate the radiative mode of the gauge field to the soft factor. So this will give a, in a sense, derivation which relates the classical classical limit of the soft factor to the waveform structure of the radiative mode of the electromagnetic field. So up to now, is there any other question?
I think people are unusually quiet. I mean, please ask a lot of questions. Don't hesitate to ask questions at all.
Okay. So now suppose consider the same scattering event classically. So suppose from the scattering event, asymptotically, you know that how particles are coming in, particles are coming out. So you know the asymptotic trajectory of the particle. Which just you can also get solving the Newton's equation in the background electromagnetic field. Scattered object. Then when you know the asymptotic trajectory, then you can, from there you can read out what will be the current density for their motion, right? So how to get the current density and all these things that I will describe later, but just suppose you know that asymptotic trajectory particles. So from there you know what will be the current density. Now what you will do is that you will solve the Maxwell's equation. So say in Lorentz gauge, you have to basically solve del rho of mu to be minus j mu, right? And that you can solve just using retarded propagator because you don't want to violate causality. So by this retarded propagator, let me write down because I think it will appear from now on many times. Square and then to the power il dot x minus y. So why this is retarded propagator? So you can see that in the complex L0 plane, the poles are always below. This is complex L0 plane. And now if you see, if suppose your x0 greater than y0, right? Then for the L0 contour integration, you have a e to the power minus I L0 times x0 minus y0. You have to do a L0 contour. And if this thing is greater, then if you try to if you try to close the contour in the, so you have to integrate along this line, and you can do using contour prescription, either closing it below or above. But if x0 greater than y0, you cannot close above, because if you close above in L0 going to infinity arc, this will divert. So you have to close from below. And if you close from below, you will get some answer which is non-vanishing. So in this range, because the pole contribute, G are not equal to 0, but say x0 is less than y0, then you have to close the contour in the upper half plane, so you will not get any pole contribution. It turns out that G are to be 0. So this is what it is telling, is that if the source, like which is the basically current density, if that is in the past light cone of the gauge field where you are computing, then it contributes. If it in the future light cone, then it will not contribute. That is the interpretation of this retarded propagator. So now using this retarded propagator, I want to compute this gauge field, but at large distance, because I put my detector at large distance. So I want 3x vector, which is R and which is large. Okay. But I directly don't want to compute the mu of x, but I want to compute a Fourier transform in the time variable e to the power I omega t of mu of t comma x vector, which I will call to be the a tilde mu of omega comma x vector. And I want to compute this thing for large x. Okay. So now if you just substitute the expression for the mu, the tilde mu omega x vector will have the expression this is standard computation of Jackson, so I think if one is familiar, one can. So what I have done, I have integrated out the L0 integration, and this is what I will left with. Now you can do, now you can like L vector, you can break into two parts, L parallel vector plus L perpendicular vector, where L parallel vector is basically parallel to x minus y vector, which is parallel to x vector minus y vector, and some L perpendicular. And you can evaluate first the L parallel vector integration just using the contour deformation and pick up the pole from this. And then you can see the integrate basically have a saddle point about L perpendicular vector equal to 0, or mod of L perpendicular vector equal to 0. And then about this saddle point, if you evaluate this integral, the final expression what you will get when x vector is, yes.
Can you explain that L parallel and L perpendicular again?
Okay.
What is it parallel or perpendicular to?
Okay. So see, to do this integration, I have to now do an integration of this L vector, which is d minus one dimensional vector. So, but this exponential contains this factor, which is I L vector dot x minus y vector.
Okay.
So I breaks it up parallel to x minus y vector and some perpendicular component.
Okay.
But this L square in the pole has both L parallel square plus L perpendicular square.
Yeah.
So first I will do the L parallel integration using the contour deformation.
Okay.
And then you can see the L perpendicular part basically has a saddle point about L perpendicular vector equal to 0, and you can evaluate using saddle point.
Okay.
And
Thanks.
doing all these things, finally you will get an expression which will look like, so I will tell what this n is. And this is some Fourier transform of the current density, with the fact that your x vector is now R a net, and your k vector or the k mu is basically minus omega into 1 comma a net. So this is the k vector will be using this saddle point approximation. It will be directed, the 3 vector of the k will be directed along the net direction. And this minus sign I am using because I have considered all the particles are incoming. So since I want to derive the outgoing radiation, so that's why the momentum sign, all the signs have changed. So there is a minus overall sign. And what is the n? So n is basically omega upon 2 pi IR times d minus 2 upon 2 upon 1 over 2 omega. So the point which I want to mention here is that you see the time if you do a Fourier transform in the time variable of the gauge field and you want to find what will be the large distance, what would be the gauge field radiative mode expansion of the gauge field, it is directly proportional to the Fourier transform of the current density associated, which you have to compute for the using the asymptotic trajectories of the particles, right? And the other thing is that why it is radiative mode, because you see it goes like 1 over r to the power d minus 2 upon 2. So this is radiative mode because using this, if you compute the electromagnetic energy at a distance r integrating over the full solid angle, you will get a finite answer. So this will be the leading radius follow. All the other follows will not contribute to energy because if you integrate it over and take r going to infinity vanishes. Okay. So this gives a relation of the gauge field to the Fourier transform of the current density. And in the last lectures, I will derive the Fourier transform of the current density in 4 space-time dimensions. And I will show that how really directly one can compute the gauge field expression to the Fourier transform the current density, and this expression will be used to what I will conjecture now to prove it. So now suppose in that way you computed what is the radiative mode of the gauge field. Now once you have, you also want that it should have a particular polarization. So you multiply by that polarization what you want and call this a new field, say phi tilde, and this becomes now a scalar. Now from this you can compute, okay, what will be the energy density in radiation energy density T mu nu. And after computing this thing for the same process of the scattering, you compute along the same solid angle delta omega what will be the energy density. So the first you compute the energy density, which have the expression like dni t I comma 0. That is what you have to do, and this involves a d to the power d minus 2-dimensional spatial integration. And if you do this thing, you see the energy momentum tensor always will be quadratic in phi, right? Because you just use the even scalar field theory energy momentum tensor del mu phi, and it will be quadratic in the phi tilde. So you have an expression for this energy density which is quadratic in phi tilde. Now you compare this energy density multiplying all the phase factor to the energy density we gotten derived from the classical soft graviton theorem, which is this sum, right? And this term you see proportional to the soft graviton factor square, at least the leading term, and some other phase factor part. Now just you equate these two energy. One is, suppose you assume you know some radiative gauge field, and from there you computed energy in the same classical scattering process. And the other way you have a from the S matrix you also take classical limit and have energy density. So you expect both energy density should be same. So if you just compare these two things, you will get a really nice relation. But this is up to some phase, because you know both the cases mod square are involved. So this is only true up to some, there can be some phase ambiguity. So you see the radiative mode of the gauge field is directly related to the soft factor, proportional to soft factor, with some normalization same in which I have defined earlier, right? So what it helps? So for a simple case, you suppose compute asymptotic trajectory, and you also derive what will be the phase factor is, and you fix once for all the phase factor. Then for a complete scattering process where you probably don't have a handle to get all this result, but if you know the soft theorem, from there you can directly write down how, taking classical limit, how to do with the gauge field. Probably it is not, it seems that very simple, because in case of quantum electrodynamics, even both computations are quite easy. Like if you can compute the classical gauge field, I think you have to give the same effort to compute obviously the soft factor. But what it tells us is that, like it's more, is that in a sense, even the radiative mode of the gauge field only depends on the scattering data. In a sense, like only particles momenta, and if they have spin, the spins and all these things. Like no theory information is needed up to some order in omega expansion for the radiative gauge field. So this is checked, say, up to order omega to the power 0 up to subleading order for the soft photon case. So up to now, is there any question? Otherwise, we'll go to the soft graviton case.
Biswajit, this will there be any discussion of? I mean, this, I don't know if this is relevant right now, but will there be any discussions of like large gauge transformations later? Like, because
no, I will not discuss on large gauge transformations.
Because this radial fall off you derived from the equation of motion, right? And this, I mean, this is something general which I don't know in QFT. I mean, I think many people in the audience might know, which is like if I do a large gauge transformation on it, like the equation of motion won't see it, but it is still a different state, probably, right? I mean, like, So how does one determine which one is the right thing to choose?
Yeah, I think that for that, like, since you are talking about first of all the classical symmetry as a large gauge transformation,
yeah.
So I think it's better to take the classical follow-ups just which you get from the solving the equation of motion.
But will the equation of motion because if I add, let's say, some del mu epsilon to this, right?
Right.
But which does not vanish at like infinity.
Okay.
Right? It changes something. Then,
yeah,
that would also satisfy the equation of motion, right?
Yeah, but I think the problem, maybe in the energy computation that will also disappear because the energy have to be finite. If it gets corrected to more leading in R power, then it will, in the R going to, if you compute energy and take R going to infinity limit, it diverges. So physical condition will tell you that how to take, maybe since the energy involves time derivative computation, so maybe time independent, like at least if there is some correction, but the correction should not be time dependent. That kind of constraint you can put.
Okay.
Leaving that, I don't know. I think if you ask me, my understanding would be whatever you get the follow-ups from the classical, solving the classical equation of motion, maybe using this kind of follow-ups analysis symmetry would be better way. But okay, I'll not discuss about the large gauge symmetry at all in my lectures.
Shujoy had a question.
Okay.
Yeah, so like, are you claiming that like radiation from any classical source, if we are like very far away, it is only made out of only soft factor?
It
we
will
have like high energy particles also,
oh,
right?
sorry. So this actually involves like only so I have not used because to relate from the leading soft photon theorem, actually one don't need the assumption because softness assumption I have not used yet, right? I have only take the classical limit.
Okay.
So in a sense, like if you in the class, you can think of that if omega corresponding to omega, if you take 1 over omega, which is basically the lambda wavelength. So if you consider this lambda wavelength is much greater than to the size of the scattering objects, right? Suppose the radius of the scattering objects, or maybe if two particles going to two particles are scattering, you can think of this is the tech parameter. So if you take the wavelength of the electromagnetic radiation to be large compared to that, then that would be determined by the soft factor or not the high energy radiations of this.
Okay.
Yes. So yeah, with the classical limit, the soft limit is also involved.
Right.
Okay.
Hi, can I make a comment?
Yes.
Following up with Subbu's question. So, this large case transformation, I mean, whatever it should obey the boundary conditions. For example, this mu going to mu plus del mu lambda, the boundary condition of mu, that is a fall off with respect to r, that is already fixed, right? Because if it goes something, the radiated mode, if it goes something other than 1 by r to the power d minus 2, let's say, so then the flux should be infinite. I mean, the flux should diverge.
I think the point which I told that if suppose the changes leading order in R, but suppose the change is independent of time, right? And the energy flux always like time derivative involves. So it may happen that if you take time derivative, that may vanish. So energy flux may not be affected. That kind of possibility is there still.
But in the energy flux, okay, I'm not sure. So, but we take a time averaged thing, right? So there also, do you take the derivative with respect to time? I don't remember that.
No. I think this TI0 expression contains this kind of terms, right? Del I of phi and del 0 of phi. This del 0 is time, and phi is, you can think, is basically the involves some gauge.
Then this del I phi, there it will be affected, right? If you have any time dependent part, extra time.
Yeah, del I phi will not will be there, but this term will be 0, right? If some time in if mu is time independent.
Yeah, that part will be 0, but
so it may not affect the energy flux. It could happen. It's just a possibility. Just trying to tell you.
Okay, but the large gas transformation, I mean, with respect to the R fall off, that is fixed. I mean, that is something we cannot change much. Is that right?
Yeah, I feel so, but there are some literatures which talks about also some overleading correction. So that's why I don't want to make some strong comment.
What I want to know is like, what is the fundamental principle that tells us that this is, because from equations of motion, if we add a pure gauge term, right, then it is also a solution to equations of motion. Okay, but we only maintain like symmetry with respect to small gauge transformations, right?
Right.
Large gauge transformations, we are like taking, let's say, one particular one out of like a bunch of them. Like we don't, once we pick one, then we don't do any large gauge transformation. So my question is like, how do we determine like which one to do?
No, I would say that, I mean, yeah, any gauge transformation will probably preserve the equation of motion, but on the top of equation of motion, you also have the condition that the energy flux should be finite, and that determines the fall of conditions of the radiative fields. Now, once the fall of conditions are fixed, then you don't have much liberty in choosing the fall of behavior of the gauge transformation parameters.
Yeah, okay, that is fine. Yeah, thank you.
But that should not impose an extra constraint on the gauge choices that I have, right?
It will not impose extra constraint, but the boundary conditions, like what should be the fall of behavior, that will be that will be restricted.
I think it should also impose, like, you know, like the way we speak of gauge invariance is usually the small gauge transformations gauge invariance. So that is the one thing which is like guaranteed in the theory. But what Arnab is saying, like as an answer to my question, is like, how do we see what large gauge transformations? I mean, if I do large gauge transformations, I get a family of solutions at infinity. Which one do I pick? So that is like not a part of the small gauge invariance that we demand in the theory.
Yeah, I think let me proceed and we can discuss. This is little debating, so we can discuss after the lecture. Okay. Now, and to study that, what will be the classical limit of multiple soft graviton theorem? So here I will study up to subleading order, because this is the thing which we have to study more and more in the next lectures. So here what will be our expectation? Here our expectation will be that the particles which are involved in the scattering, so I should call maybe they are classical objects, so they are macroscopic objects, right? And we would expect that the macroscopic objects are large, that their mass is large in a sense, or if they are massless, their energy is large in compared to Planck energy, or if their mass is large in compared to the Planck mass. Like scattering of two neutron star, one neutron star, one black hole, or such kind of processes. And their mass is obviously much larger than the Planck mass. Planck mass is some microgram order. So one of the things in the classical limit is that we have to consider this pi. So this is suppose order lambda, and this lambda is much greater than the Planck mass. Okay. The other limit, which is basically the classical limit, the angular momentum, right? So we have an angular momentum expression in the subleading soft factor, which is like pi mu del pi nu minus pi nu del pi mu. So that orbital part in the classical limit, you can think of we can replace I del pi mu by the trajectory of the particles Ra mu. Right? So in a sense, this basically gives us like I pi mu Ra nu minus pi nu Ra mu. This will be the classical angular momentum, and we will call this thing to be actually R cross P is the classical angular momentum. So minus I times, this is the classical angular momentum of the ith particle. So this is ith particle trajectory also. Mu nu. So this is the classical. We have to replace the orbital angular part to be this expression, which is the classical angular momentum. Now, once you write down the subleading soft factor, which was the differential operator in terms of this classical angular momentum, now S0 and S1 commutes. Earlier, what happens is that S1 does not commute with S0 because there is a differential operator. But in the classical limit, since this becomes just a multiplicative factor, so now S0, S1 commutes. This is just a side comment, which will be helpful in the later discussion. So, and we can try to determine that what will be the order of this classical angular momentum, say. So asymptotically, okay, let me maybe in higher dimension, let me write down what will be the expression, asymptotic expression of this classical angular momentum. So in higher dimension, suppose the trajectory of the particles, xa mu, sigma is the proper time, goes like pa mu upon ma, sigma plus some ca mu. This ca mu is basically, you can think of the contains, the zeroth component contains the time delay with respect to one of the other particles, and CAI you can think of is the impact parameter, the distance between one to the other particles at the scattering center. So this is like, in a sense, covariant impact parameter, you can say. Now if you substitute this thing in the expression for the classical angular momenta, what you will get is basically this factor will cancel among themselves, and you will find pi mu Ca for ith particle nu minus pi nu A for ith particle mu. This is the classical expression for the angular momentum, right? And you can try to determine what would be its order. Like for example, suppose two black holes are scattering, and suppose their impact parameter is in order of their Schwarzschild radius. So then obviously P already I told to be order of lambda. Then what will be the CA order? So CA order, you can see that the CA order will be like basically the order of the Schwarzschild radius, and the order, like if the mass is also scale like m, lambda, which is the momentum scales like, then you can think that C basically scales like, I think one can figure it out from the Schwarzschild matrix, say 2gm upon r to the power d minus 3 dt square. From there one can figure it out, r to be m to the power 1 by d minus 3. So C turns to 1 by d minus 3. This is the order for the C, and then J has a extra lambda multiplication. So it is fine how I was talking about the classical limit. Now I have to take the soft limit as well. Now in class, like gravitational radiation, what do you mean by soft limit? So the soft limit, what you see is that the characteristic scale of the scattering, which is in order of impact parameter or the Schwarzschild radius, so that the wavelength of the radiation should be large compared to that, so that you can treat them as kind of effectively particles are scattering. So what we want is that lambda, the wavelength, which is 1 over omega, should be much greater than the Schwarzschild radius, which is 1 upon lambda to the power 1 upon d minus 3, right? So we can define a softness parameter beta, called softness parameter, which is beta is much less than 1, and you can define your omega to be order of beta times lambda to the power minus 1 upon d minus 3. Right, so this is what we will call the soft limit. This is when beta is much less than 1. Now you substitute all this order, like the order of omega and the order of the classical angular momentum and the order of the momentum of the particles in soft factors, in the multiple soft graviton factor. Okay, so for that I need to go back to the multiple soft graviton factor, which we have here, say. So these are our multiple soft graviton factors. Different terms are written here, and we can try to analyze how the different terms goes like. Okay, and if you see, it turns out, so let me write in the top that this leading soft factor S0 that goes like, for a particular, say, fixed beta, we fix the momentum of the gravitons, which we want the gravity wave energy. So fixed beta, softness is fixed, but small number. You can see that the S0 goes like d minus 3 upon lambda to the power d minus 3 upon d minus 2. Sorry, I am wrong. If you compute it. You'll get lambda to the power d minus 2 upon d minus 3. And you can see that S1 also goes like the same way. Same, like lambda to the power d minus 2 upon d minus 3. But if you try to analyze the contact terms, you will see that the contact terms goes very less. Like this full contact term, if you try to analyze, actually it goes like d minus 2 upon d minus 3, the same factor. Now you see what is the difference. So the leading soft factor is anyway leading. That's fine. Now let's compare the S0 to the power m piece and the S1 S0 to the power m minus 1 times S1, and the rest piece is basically contains m minus 2 number of S0 and the contact piece, right? So basically I have to compare S0 S1 to this contact term, and this S0 S1 basically you can think of this basically twice of this power, whatever the contact term is. So in large lambda value, S0 S1 is always dominating than the contact term. So in the classical limit, we can drop the contact piece. Okay. And the other thing is that now since S0 S1 perfectly commutes among themselves, so actually now I can write this thing to be basically multiplication of m number of S0 plus S1 terms in the classical limit and leaving the contact terms in the rest m. So in the classical limit, the multiples of graviton theorem one can show can be written as so 0 is for the leading soft factor, 1 is for the subleading soft factor with polarization epsilon r and momentum k times this gamma n. Where this S r the subleading soft factor, there is angular momentum factor that one have to think of as a classical angular momentum. Okay. So this will be the general expression in the classical limit. Now, once you have a classical limit general expression, you use the same prescription to like also like now you fix a beta softness parameter, which is a particular momentum, and then particular momentum for the soft graviton, and then along a particular direction you want to compute what is the gravitational radiation. And in the same way, you compute energy from the soft theorem and energy from the classical gravitational radiation. And what you find a similar expression. Let me write it down. N is the same normalization factor what we have, and this is S0 GR plus S1 GR up to some phase factor. Now you see in a general classical scattering process, gravity is a nonlinear thing, and to compute the classical gravitational radiation, you have to use some Green's function, which is even not like the flat space Green's function, very complicated thing, and from there try to do expansion in omega, and it's very hard to compute gravitational radiation in general scattering process. But up to some order in the omega expansion, if you know the soft theorem from the soft factor, you directly can read out what will be the waveform of the gravitational radiation. So this is the nice thing in the large in the wavelength limit. You can always, like up to some order in the omega expansion, you can always read out the gravitational waveform at large distance in terms of the soft graviton factors. So is there any question?
Biswajit, there are questions, but they all have to do with large gauge transformation, so we are not bothering you.
Okay. So I think one thing which I want to mention here is that one subtlety which I actually dropped is that when I cancel this contact piece, so you can see that this other terms has single sum over the soft gravitons, but the contact terms are two sums of the soft graviton factor. And for that, this involves m number of terms in this expression, but this involves a pair, so m into m minus 1 by 2 number of terms, so large m it is m squared term. And so you can think of that even each term probably suppress whether sum over the m square number of terms relative to sum over m number of terms corresponding to this could be suppressed or not. So for this, one actually needs to also assume that one of the assumptions which I not mentioned, but this is subtlety, that the m into omega, which is the total energy for the gravitational radiation, should be small compared to each of the particles, say mass or energy, maybe EI. Maybe there is more covariant way one can say, but roughly this is the picture that if finite energy particles have energy EI, so to make sense to drop the contact terms, one also have to assume that the due to m number of graviton emission, whatever the gravity wave you are having, so this has like this can be related to the soft factor, and soft factor only if the gravitational radiation, low energy gravitational radiation, have the total radiation energy have to be less compared to the each particle's energy. So if not this happens, then you allow that all the radiations in the sum over the I particle, they consider this as a hard gravitons, and only take care of the small energy gravitons which sum does not comparable to the energy of the finite energy particles. So you can incorporate in the sum of the hard particles energy at hard soft gravitons. So that can happen in like black hole merger problem where strong gravity is affected. So large number of gravitational radiations comes out, and obviously those are not each, though each of the gravitational wavelength is like in order of, so maybe in order maybe less compared to the each black hole's mass, but the gravitational energy which come out in this process, so that turns out to be really large. So that is why one have to think of that this there is, you can put a cutoff that after which the energy of the gravitation, like hard gravitons, you treat up as a sum in the sum over the finite energy particles. So this is hard gravitons, and below certain range. So I will explain in detail for some examples that you can take those at the soft gravitons, and only in that limit you can apply our formula. So this also can be achieved in two kind of processes. One is, suppose a 2 going to 2 particle scattering is happening. So this is called the large impact parameter scattering. For two going to 2 particle, or you can think of as a, like there is a large object, black hole is there, and some test particle is coming in the background and going out. So this is called the probe scatterer limit. Probe scatterer limit. So in these two kind of cases, actually it has been tested that this relation which is proposed, the relation between the soft graviton factor and the gravitational waveform, one can test in general dimension. So I think up to now, if there is any question I can take, otherwise I will proceed.
Biswajit, I should say that you have 7 more minutes.
Okay. Okay. So if there is no question, I can proceed. So, okay. So we have discussed that there are some problems in 4-dimensional S matrix, probably how to define even 4-dimensional S matrix for infrared divergence, it is not clear. But can we, even if we don't have understanding of the 4-dimensional S matrix, can we expect some classical limit of soft theorem, or the classical, we know that the classical gravitational waveform is anyway people have derived from in black hole merger problem. So probably classical limit, like the classical gravitational waveform still makes sense. So why not we start from the naive assumption that, okay, maybe the higher dimensional soft graviton theorem in the classical limit is still valid, and try to get that whether we can make sense of some soft factor in 4 space-time dimension. So the question which I want to ask is that, from our understanding of classical limit of Soft theorem in d greater than 4, can we extract some information for d equal to 4 Soft theorem classical limit? Though we don't have yet, I have not shown what is the Soft theorem for d equal to 4. So that is the question which I want to ask, and I will tell that where the problem is. Maybe we can resolve in the next day. So you see, let's see what is the expression for the quantum subleading soft graviton factor. It has the expression and so I'm just leaving the spin part for a moment. So this is pi nu del pi rho minus pi rho del pi mu and some spin part. Okay, so some spin, say neuropiece. So this is roughly the structure of the subleading soft graviton factor. So now in the classical limit, what we told is that you replace this factor by classical angular momentum, which is minus I times Ra for ith particle mu pi nu minus Ra nu pi mu, right? Now I have to substitute the trajectory of the particles in d equal to 4. So the question which we want to ask is that what is the trajectory of a particle in d equal to 4 under gravitational interaction, long range. So in 4 dimension, you know that like gravity is a long range force. So even if you solve that, okay, suppose even solve Newton's equation with the potential, you know, gravitational potential goes like gm upon r, probably some sign, and you can try to solve, okay, how the how like at radial distance r, how the trajectory of the particles could look like. So you just solve in a sense d square r dt square to be minus del v del r. So basically you will get d square r dt square goes like 1 over r square. And you want to solve that at large t, that is suppose t going to infinity, how the nature of the trajectory is. So if you do this thing, so suppose you assume that the trajectory, asymptotic trajectory, is like a straight line trajectory with momentum pi, that is in scattering, we assume that always the asymptotic particles asymptotically have a particular momentum. So asymptotically, you may assume that, okay, let me assume that Ri mu is some pi mu upon mi times some sigma. Sigma is the impact parameter plus some constant Ri mu. But you can see that if you do take second derivative, so let me just take naive dt non-relativistic limit. So that basically will give you 0, right? If you take like if you think of this sigma to be time t non-relativistic limit and replace basically r0 by t and do this thing, it basically gives like 0. So it cannot have a straight line trajectory. Like it is 0, but you know that in here you will have a 1 over r squared term. So 1 over r square basically is large sigma goes like 1 over sigma square or maybe 1 over t square. So you will have equation d square r dt square goes like 1 over t square, and this could only be satisfied if r has a log t piece, right? If r has a log t, then you will have a d square r dt square to be 1 over t square. So that means your trajectory is not now a straight line trajectory, but you have a correction. say let me call this, so this is I called there CA mu, so let me call this some d I mu times log sigma. Okay, so now in the classical soft vector, I have a expression for the classical angular momenta, which is Ri mu sigma Pi nu minus Ri nu Pi mu. But now you have a trajectory, which is Ri mu has a log term, right? So it has some Ci mu plus some Pi mu upon mi sigma, which is the constant velocity, and with this you have a log term, which is I called it di mu log sigma. But now if you substitute here, what you will get in d equal to 4 is that it have Ci mu Pi nu minus Ci nu Pi mu plus di mu Pi nu minus di nu Pi mu times some log sigma. And you see at sigma going to infinity, di mu nu also goes to infinity. So we are facing problem that the soft factor diverges. So now you see in fourth space-time dimension, the soft factor diverges at log of the sigma because the subleading soft factor contains a classical angular momentum piece. Right, so this is a real problem. So we have to cure this problem because we know that we have a relation between gauge field expression, right? Say E tilde mu nu related to some soft graviton factor between S0 plus S1. And this thing at large sigma in d equal to 4 goes like log sigma, and that goes to be infinity. But we know that in general, like classical scattering, if we have a black hole scattering, we know that there is a finite gravitational waveform. Right? So there is a clear contradiction between them. What goes wrong in the soft factor? Because classical analysis, we know the independent classical analysis, this is fine, but we have a given a relation where this is related to some normalization times soft factor, and this soft factor diverges. So there is a clear contradiction, and we have to make a resolution. We have to give a resolution to this thing. And this I will discuss in the next lecture. So is there any question up to this point? Or people are still busy in
okay,
okay.
Let us thank Biswajit for this lecture. So if there are any pressing questions, people can ask now, or otherwise we will pause the recording and people can ask questions more informally.
Biswajit, so regarding this 1 over omega fall off, so
right.
Were you saying that like if there is some, unless there is some time dependent transform, addition, it won't change the omega behavior? Is that what you were saying?
I have not told any omega behavior. So
no, because like you were saying that for the energy to be the same, the large gauge transformation should be time independent. Right?
Okay. Yes.
So then probably they won't affect the frequency behavior because it's a time independent addition to the gauge field, right? So then probably your 1 over omega fall off is just fixed. Because
yeah, this may happen. Yeah.
Okay. Okay.
Yeah, but okay, I don't. Is there any question after that what I discussed about this 4th dimension? What is the real problem is?
Or from earlier part also.
Or from the earlier part also. In higher dimension, how the classical and the quantum, like from the quantum soft theorem, how to take classical limit and relate it to the waveform.
I think maybe we can pause the recording.
Yes,
let people ask more freely and informally. Okay, so let us thank all the speakers for today, Biswajit and Subhu both, once more.